Today, I think a lot of the maths that we're going to do is going to be beginner friendly. I've tried to keep this quite beginner friendly. What we're going to do is we're going to do Robert Boyle. We'll talk a little bit about Robert Boyle's history, and we'll talk about, in parallel, his comrades. The next guy we're going to look into is kind of a funny guy, in the sense of he didn't really do a whole lot, but he is the reason why we gave the word electron its name. Electron. It's from Stoney. Stoney is an Irish physicist as well. He did a whole bunch of stuff, quite humorous. But we'll talk about the electron, electric field, and potential. Because building on that, we are going to talk a little about the first particle accelerator that was created by Walton and Cockcroft. Walton was an Irish physicist, and he won the Nobel Prize for successfully splitting the atom. He split the lithium atom specifically by targeting a proton on it. So that was the first accelerator. Maybe you guys have heard of the accelerators in CERN, the Large Hadron Collider, for example. So where it all started was thanks to an Irish physicist. And then we're going to end with technically a chemist, but if anyone knows me, everything is physics and everything is just a model of physics. It doesn't matter what you study, what you learn, what you do. Everything is a model of physics. And what we're going to do is we're going to talk about Kathleen Lonsdale. And she was the lady who discovered or proved, because there was theories and ideas about this, that the benzene ring was in fact a ring. It was a flat shape. And she used a method called X-ray diffraction. Come on and Herder, thank you so much for setting up a tofu laboratory mug. Okay, so it's a mug like this, but with my lab all drawn on it. If you guys want to enter, press ! Enter. Anyone can enter. Anyone can win the mug. I hope you enjoy the wonderful artwork and merch. So everyone just type in ! Enter and you have a chance of winning a mug with a drawn tofu lab on it. I'll show you what the lab looks like. Let's talk about some really cool physics. The cycler. That's the lab background. Oh, George, I'm happy. I'm happy to hear that. Sorry, while that's finishing, she did X-ray diffraction, and so we're actually going to do that experiment with the laser. We're going to show the diffraction and how we can calculate the distance between atoms. So we're going to do an actual experiment of that today. Hotan, I'm so glad you got, a newcomer got a merch. Welcome in, and I hope you enjoy the wonderful mug of my lab drawn on it. Dan, I have no idea why I decided to apply to the front page at 8 o'clock in the morning. I just thought that because it's St. Paddy's Day, I'll treat this as a work day and get up at 7 like I usually do, stream at 8, finish at 4 like a normal work day. Yeah. So today I don't get to work in Ireland because it's St. Patrick's Day. It is an international holiday here. Very important. And so because, it's a national holiday, a bank holiday, which means that schools, universities, everything's closed. That's why I'm not working today. Instead, I'm working with you guys. Okay, so I think there's nothing stopping us from kicking off the lesson, unless anyone wants to stop me. No? I'm almost finished my coffee. I'll probably grab water soon. Have fun with physics. Take care, Ninja. Yeah, it is a weird time for many people. So, we're going to start our story with Robert Boyle. I took just a couple of notes because some of the scientists I don't know too much about. I know a lot about Robert Boyle. But Robert Boyle... Can I go to the bathroom first? Quick! So Robert Boyle was actually born in a county called Waterford. It's on the south part of Ireland. And he was of Protestant descent. This was a time of when English had taken over Ireland. Many years. A lot of years. So do be wary that this is just an unfortunate part of Irish very, very long history. And he is dubbed as the father of modern chemistry. Despite being a physicist, he is dubbed the father of modern chemistry. How should I say this? Everything he did was obviously studying physics, but when I mentioned this earlier, that everything is really just a model of physics in the sense that chemistry always, especially initially, just branched off from physics. When you need a certain thing to work, or you need a little realm of your research to work in a certain exact way, you can just create a model that works for your story. And that's why when we study the electron and we study the atom, we have all these different rules and laws and models. We have the Bohr model, the planetary model, Rutherford's model, J.J. Thomson's model. There's all these different models. And the idea behind this is it doesn't matter which one you study, as long as the model that you've developed truthfully always works for you, no matter what. So just be wary about that. And when you hear one person say, this is the model, I'm right, and another person will say, no, I'm right, this is my model, don't listen to them. They're all pretentious. Everything is just physics. Now, Robert Boyle was a really cool dude. Himself and Hooke, Robert Hooke, another Robert Hooke, from Hooke's Law, if anyone is familiar with him, developed to what is known now as the Royal Society. Right, God, I'm not sure how to answer that question, by the way. And so what he was studying vacuums. He was trying to create a vacuum inside a glass jar, and Robert Hooke, famously, helped him create the first air pump. So the air pump was a machine, well, a little mechanical thing, to push out air from a enclosed enclosure. That was a very redundant statement. Happy St. Patrick's Day. Welcome in, everyone. Welcome in. So he worked really hard to pump out all the gas inside of a glass jar, and he did a whole bunch of experiments. Now, obviously, to many of you who've studied physics, you're jumping ahead and like, oh, volume, oh, pressure. This was 1,600 after-ish. Good bit after-ish. 1,700? A mine. Wrong town. Thank you so much. You're very, very kind. Let me double check when Robert Boyle was born. He was born in 1691. He was born in 1627 and died in 1691. So just before the turn of the century. Vacuum research sucks. You know what? Fair point. Fair point. To put it in a time perspective, Newton, Boyle, and Hooke were all in the same circle. Now, Newton was, known for being kind of, not very social and stuff. But how should I say it? He wasn't very social, but they were still his peers. Robert Hooke famously kept correcting his literature and kept saying things, to degrade Newton, and he wasn't very, very happy. I think there was a bit of jealousy, unfortunately. But as far as I know, Robert Boyle didn't actually get involved in the drama between Hooke and Newton. I don't know of any drama. Maybe. Yeah, maybe someone can jump in on that one. Welcome in, everyone. Do you do astrophysics? No. I do electric grid stability, battery technology, and wind turbine integration. And I teach things like electrical devices and thermodynamics. So yeah, I'm a very old school physicist, if that makes sense. Okay, so Robert Boyle developed the air pump, or Hooke helped him, and they created a vacuum. So what could you do in a vacuum? Well, what he discovered was that sound doesn't travel through a vacuum. Do you guys remember maybe in primary school, there was a bell inside a vacuum, and when there was air in the bell, it would ring and you could hear it. But then if you remove the vacuum, you couldn't hear the bell anymore. That's because there's no air molecules around the bell and they couldn't vibrate and vibrate all the way to the glass. And so you couldn't hear it. So that is where that original experiment was performed. The next one that he did was that flames go out without air. Now that was already kind of had vibes about this already, but it was a confirmation that you did need air. Didn't know about oxygen yet, by the way. You did need air for a flame to work. So in a vacuum, a flame was put out because it had no oxygen to burn. And last but not least, another experiment that he did was he put animals in there. I know, don't come at me. But yes, he did have to test this, and animals did not survive in the vacuum. And so with that conclusion, and this helped with space travel, they knew that humans couldn't survive in a vacuum without protection. So maybe the most literal take on the medium is the message. Probably. Thank you again, Wrong Town. Whoopsie doodles indeed. But like many of his peers, Hooke and Newton and so on and so forth, big believer in science, but also a big believer in religion. So a lot of the things is, you know, based on that. There was a lot of conclusions kind of made in that realm.
And they call it a mine.
Yours truly, Leon.
Mine.
Thank you for subscribing, number 1. Number 2, thank you for subscribing for 6 months. And number 3, I love Leon S. Kennedy. So the fact that you're yours truly, Leon. Thank you so much for your support. You're very kind. Thank you so much for... Wait. Before anyone subscribes, especially new people, chat, there is a terms and conditions if you subscribe to this channel. If you subscribe to me, you will sign a contract saying that you are willingly donating your body to science. You become a lab rat and we do experiments on you. And if anything were to happen to you, I take absolutely no blame for it. Okay, good. I'm glad we covered that. Sorry, yours truly, Leon. I probably should have mentioned that before you subscribed. We are coming to the whiteboard. Yes. Bringing out the whiteboard to teach. Can't do it without it. I wish I had a blackboard. That would be a dream. Might move the camera this way. Like how Jeremy's in the shot. Great. Ugh. There we go. Get the chalk as well. There was fine print on the contract. There was. A few people have been complimenting the artwork, the new frame, and obviously in the starting screen we had me dressed up as very, very Irish, and then Bambi in a little hat. All the artwork is by Medjay in the chat if you guys are interested. And I do not do any of the artwork. I don't got the skills, unfortunately. Okay, so what I'm going to do is I'm going to talk about Boyle. Okay, I'm going to mention his story, but then... Beep, beep, beep. Thank you so much for subbing for 3 months. Really appreciate that.
Mine.
Oh, mine. Oh, really appreciate it. And you read the fine print in the contract. Thank you. Where was I? Boyle said something very interesting when he created the vacuum experiment. He noticed that pressure was inversely proportional to volume. Now that symbol here kind of looks like an alpha, means proportional. And inversely means we flip it upside down. If a V was on its own, that's directly proportional, but then 1 over V is inversely proportional. It's a very, very interesting graph we're going to get. We'll do this experiment. So as you know, the volume was decreasing, the pressure was increasing, but it wasn't a linear relationship. It was very, very interesting. So what we're going to do is, before we do this experiment and prove Boyle's law, I'm actually going to teach you something else. So minus sign is just a negative slope, foobar. Inverse means inverted. That's where it gets it.
Back on the menu, boy.
Inverse just means flipped upside down, and opposite or negative would be the minus sign. Commander Herder, thank you so much for gifting 100 bits and kicking off a hype train. You guys are amazing. Thank you, thank you. So many people are coming in and saying hello and seeing that they're really, really interested in physics. I'm really glad to hear it. There's lots of people chatting though, so I apologize for not keeping up with everyone. Apologies. Okay. Pressure is directly proportional to 1 over V. And over the years, a lot of people chimed in. They found out that, well, temperature is directly proportional to volume. What does that mean? Well, that means as the temperature of a gas rises, the volume of a gas rises. So that's kind of interesting.
Looks like meat's back on the menu, boy.
Thank you so much for the biddies. Another thing that was discovered was that pressure was directly proportional to volume. And then the final guy who came in to put all of these guys together is a gentleman by the name of Avogadro. Do not confuse with avocado, because every time you'll try to type Avogadro on your calculator, or sorry, on your phone, it will autocorrect to avocado. Loads of avocado jokes. Oh, I'm glad to hear that, Thomas. And thank you so much for the 100 bits, Zeus and Wayno. You guys are amazing. Thank you so much for the kindness. You're very, very good. Hello, Bog. Welcome in, welcome in. All fear the Bog. So pressure decreases, volume increases. Exactly. That statement is correct as well. So Avogadro came in and he said something very interesting. He said that the number of particles present was also a constant. Now, he introduced the whole concept of a mole. 1 mole is 6.022 by 10 to the power of 23 molecules and 16 grams of 12 carbon. We're not going to go into that because that's not the point. For now, I just want you to trust me. For now, we're all just saying, trust me on this. And the final equation that came out is this. PV is equal to nRT. P stands for pressure. The unit for it is also after a famous scientist, Pascal, PA. Volume. The SI unit, SI means the scientific base unit that we tend to use, is meters cubed. I know that our freedom friends might not appreciate that, but it is what it is. It is what it is. T is temperature. And the unit that we use for temperature is really, really important. It's called Kelvin. Now, so many of you guys are going to jump in, but the unit for temperature is Celsius, but the unit for it is Fahrenheit. Pedro Pascal. Exactly. So the unit that we use in science is Kelvin. And the reason why is because, well, if I have zero pressure, I have nothing. You can't go negative. Yes, you can go negative gauge pressure, but you can never go negative absolute pressure. You can't have less than zero volume. Zero is nothing. So there we go. But temperature, if I say it's 0 degrees, me and you both know that it can get colder, whether in degrees Celsius or in Fahrenheit. The reason why we use Kelvin is because absolute zero is the coldest possible temperature. 0 Kelvin is an absolute zero, and that is why you have to use it. This equation only works if all these guys, when they reach 0, pretty much means nothing. Happy St. Patrick's Day. Welcome in, Nordic Gal. Hopefully. Oh, not even Gal. Sorry, Gail. Apologies. I wear glasses for a reason. I can't read. Exactly. And it's minus 273.15 degrees, as Zach mentioned there. Yes, I should mention, especially since it's St. Patrick's Day, that we're not big fans of Kelvin, I discovered recently. Because Kelvin got his name to be Lord Kelvin because he opposed Home Rule in Ireland. Now, only the Irish people will probably understand what that means. So I'd just like to mention, we even though Kelvin is a good temperature and it's a great temperature, kind of controversial these days. Because that's net kinetic energy where there's no movement of particles anymore, Krypton. That's kind of the base story. It's the bare minimum where the particles stop moving. Okay. These two I didn't talk about. This guy is a mole. If you have 1 mole of a substance, it means that you have 6.02 by 10 to the power of 23 molecules. So 1 mole is equal to 6.02 by 10 to the power of 23 molecules. Can someone chime in and actually check that? I just remembered it off the top of my head. I don't actually remember if that's true. Oh, the light is glaring. That a little bit better. I think that's a little bit better. There's less glare. Yeah, that's better. Yeah, it is that value. Thank you very much. And last thing is, we have something called an ideal gas constant, and it's just to kind of make the equation all work. We have a lot of these kind of constants. It's a little number lobbed into equations to make them work. So maybe if you studied Newton's gravitation law, F is equal to G times M1, M2, over R squared. That big G is a gravitational constant. Oh no, the sub-alerts are broken.
And they call it a mine.
Bloons, thank you so much for gifting 10 gift subs to the community. And breaking my breaking my alerts.
I don't know half of you half as well as
Thank you. You're very, very kind.
Less than half of you half as well as you deserve.
You're very, very kind. Chat is just trying to distract me. Welcome in, guys. Sorry for the disruption. Well, listen. You know, it's like that student in school who who's a messer but is very, very nice as well to the teacher. Why was 6.02 by 10 to the power of 23 chosen as a number for a mole? Where does it come from? Great question, Brand. It actually comes from carbon 12. If you look at the periodic table of elements, so you look at carbon, 12 grams of carbon 12 has an exact amount of 6.022 by 10 to the power of 23 and so on and so forth. When we made SI units a couple of 100 years ago, we grabbed a thing. Here we go. I'm kidnapping Jeremy. I picked up Jeremy and I said, Jeremy, you are now 1 kilogram. You are the definition of 1 kg. Everything in physics and the universe and engineering is going to be based on Jeremy's head. Now, that was a bit problematic because, well, over the years, poor Jeremy is going to degrade. He's quite biodegradable. He's good for the environment. But Jeremy will degrade over time, and that's not very good because if he degrades, he's going to lose mass, and so the definition of the kilogram is changing with time. That's terrible. So what we did with SI units, there's 7 base SI units, is there was a physical thing that was determining what it was based or measured on. And so what we did was we ended up working backwards. We said, okay, we need to associate the kilogram, the meter, the mole, everything with some sort of physical constant in the universe. And so that's where, as of 2019, this is really new. This is quite new. And it was a huge change in the world of science. All the constants, all the SI base units are now associated with constants and all go back to time And the second is defined as something crazy, and we're not going to cover it today. But is it cesium? Yeah, it's based on the emission of radiation, oscillating radiation of cesium. There we go. But yeah, there's a few SI-based units. So there's the kilogram for mass, there's meter for distance, second for time, mole for amount of molecules. This one is controversial. A lot of people don't like this to be an SI unit. Mole, the luminosity one. Where's the other two? Oh, ampere, and one more I'm missing. No, not volt. Not magnetic, no. I loved Interstellar. What is it again? Candela is the luminosity one that I referred to. Candela, kilogram, meter, second, mole. Kelvin, amp, thank you. Okay, there we go. We've got there eventually. We have it right up here as well. Sorry. Okay, temperature is hot. It can be. It can be. You know what? Jokes aside, do you realize how much work it takes to define what hot is in physics? There was like battles, bloody battles between physicists to define what hot was. Okay, so PV is equal to nRT. This is what we call an ideal gas law. And the reason why it's called an ideal gas law, well, chat, shocker. Hold your pearls for this one. Hold on to this. It's because it's an ideal situation. No gas is ideal, but they get pretty close to it. And an ideal gas is something that doesn't take up a space by itself, that all the collisions are elastic. There's all these little conditions. It's not perfect, but it's a pretty damn good approximation. So because it's a pretty good approximation, we use it in almost all calculations, and especially in thermodynamics. So PV is equal to nRT, and that is the ideal gas, which means that we're going to perform an experiment today with this machine. So this machine, I'll bring it up a little bit closer. As you can see, I have a little syringe here. The syringe is going to be changing the volume for me. This guy is a pressure gauge. I'm going to open and close this pressure, and this guy over here is a temperature reading. At the bottom of this gas right here, we have a temperature sensor. So if this works actually, let me close the pressure for lols. I'm gonna swing this really, really quickly. The temperature's supposed to be decreasing, but I can't swing this fast enough. This doesn't work very well in this case. So the idea behind it is when you unscrew this volume, as the volume increases, the temperature is meant to decrease according to this law. But the problem is that it's just plastic. It's dissipating very, very quickly. This is just a gas apparatus. Yeah. So that is the form, exactly. So part one of this experiment right now, what we're going to do is we're going to measure this. We're going to prove this. Then I'm going to trap some gas in here, and we're going to sit down and we're going to calculate the amount of molecules that I've trapped in here. So that's what's going to be the plan. If you guys are okay with that, I'm just going to grab some drink them real quick, or water even. Yeah, I need water. Okay, apologies about that. My coffee finished, and I always like to be drinking. That sounds bad, especially as an Irish person on St. Paddy's Day. That's not what I meant when I said drink. Don't come at me. Ugh. What is the early morning? I know. It's so early in the morning. So what I'm going to do is I'm actually going to move my keyboard and mouse and everything. I'm going to set up on another overlay. And what we're going to do is we're going to do this Boyle's Law experiment live on stream. And I'm going to encourage chat to participate in this. If anyone has Excel or a knockoff version of Excel or, you know, the online version, whatever it is, a spreadsheet, we're going to have two columns. We're going to have volume column. We're going to have a pressure column. We're going to do some maths, okay? I'm going to bring the camera down. Like I said, let me go into my building stream overlay. So it's this guy. I'm going to bring the camera down so you guys can see this a bit better. Science before 9 a.m. I know. I'm sorry, Evandriel. I'm sorry, hacks. You guys can see the results of this experiment quite well. Now, you guys are at a bad angle to read the volume because remember the meniscus? Have to read it at eye level. So we'll do the best that we can. Here we go. Oh, and I'll turn on my other camera. Isn't that what I was meant to do? I have another camera here. This is the HD webcam. Oh, working. This is the wrong streaming overlay. This is my programming overlay. I swear I thought on this overlay I had my second camera. Okay, it's just not working. Doesn't want to work for me today. That's fine. You don't need to see me. Okay, so what I want you guys to do is open up Excel. And I want you to make two columns. One for pressure and one for volume. Okay? So pressure is going to be in pascals. And volume is going to be in millimeters. Oh, sorry, in milliliters. We're going to do some conversions. Don't worry about that. We'll do conversions, I promise. We have to do everything in SI. But for now, we can, you know. Of course I'm not using PSI. That's not SI. So, let's get this guy switched on. I'm just going to make sure that the volume is at the top part. Oh, here we go. Okay, so we're starting at 65 mils. I'm going to turn on the temperature reading. We're just going to monitor that the temperature remains relatively constant. We'll take on the average. No, millimeters of mercury is so old school. No one uses that. No. We don't use that anymore. I like to teach it. It's quite nice, but it isn't relevant. So I'm going to put this up a little bit so you guys can see this a little bit better. So as you can see, we're starting at 65 milliliters and our pressure gauge is reading 0. Now look at that unit. HPA. What does HPA stand? Does anyone know? HPA. Hectopascal, that's right. Hecto means 100. So if it moves to, so basically whatever number we get, we're going to multiply by 100. But let's just keep track of the hectopascal for now. It's hard for us. HPA. Lowercase h, it's a prefix. So just to be aware, hecto is a prefix, same way as kilometer, kilo is a prefix. Millimeter, the M, milli, is a prefix as well. They're all the same thing. No, they're different values, but that's what a prefix is. Okay, so I've closed the valve. I've trapped the gas inside. So here we go. Let's decrease our volume down to 55. Or let's do each 5. Let's go to 60, okay? There we go. We've moved to 60. A little bit more. And the pressure only moved the tiniest bit, okay? It moved about 1 bar. So let's say, what is 1 bar? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 500 divided by 10. So each bar is 50 hectopascals. So each bar that it moves, each one of those tiny bars, is going to be 50 pascals. So I want you to write in Excel 50, or I suppose the first one is 0 hectopascals for the volume of 65 mils. And then it was, how many hectopascals? 1. 50? 50 hectopascals. And it changed to 60 mil. Okay, that's fine. I'm glad. Did you go back to 0 now? No. So I started at 0, but we're not going to go back to 0. Okay. So we're going to move. Yeah, the angle is weird. So the camera is. I'm trying to place this perpendicular to the camera so you guys can see it a bit better. So we're going to move this down now to 55. Let me get a better look at my own angle here. Yeah, that's 55. So 55. And how many hectopascals is that now? Better. 1, 2, 3. So 150 hectopascal. So when it went down to 55 mils, we got 150 hectopascals. Yeah, the pressure, it's actually quite interesting how much pressure is changing. And hopefully it'll change significantly more because again, it's not a linear relationship. So we're going to go down, all the way down to 50. Yeah, that's 50. And we got 1, 2, 3, 4, 5 multiplied by 50 is 250 hectopascal for 50 mils. Okay, we're going to keep going. Keep on going. The temperature's going up. The temperature sensor isn't that great. It is just fluctuating and the room is heating up at the moment, Zir, so it's just passively heating up. The sensor is right here at the bottom and yeah, it's not going to be great. It's just going to be an average temperature we're going to take. Whatever temperature rise that occurs inside the sky is just going to dissipate very, very quickly. So you can see as the volume decreases, the pressure might have increased a little bit, but you see it drop down immediately. It's because this is just plastic and it dissipates very, very quickly. Oh, I'm glad to hear that, Mixir. Yeah, no, I'll try Soul Reaver. It is a fair point. The light is catching it. Actually, I might just turn off this light. Oh no, it's too dark without it. Yeah, no, sorry. I need to do that. Okay, so need to move it down a bit more. At 45 mils, the pressure gauge reads 9 multiplied by 50 is 450 pascals, hectopascals. 450 hectopascals for 40 mils. We're halfway there, chat. Whoa, we're halfway there. Want to move down to 40 now. As you can see, the temperature jumps up a little bit. Volume and temperature. Which law is that? Volume and temperature. That's Charles' law. Charles was into hot air balloons. That was like a popular hobby back in the day. That was a very important thing to notice. 1, 2, 3. That's 650 hectopascals. 650 hectopascals for 40 mil. Maybe you guys are noticing a little trend. I'm going to decrease this down again. Getting a little bit harder to actually screw the screw top now. What does it say here now? Oh, it jumps significantly. Holy smokes. Whoa. That's 850 hectopascals now. We'll look at this graph in a second, I promise. I'll show you the graph as well in case anyone wants to try this themselves, you're more than welcome to as well. Oh, Zetron, absolutely. I don't have a whole bunch of young people in my community. Most of my community, I'm so sorry to call my lab rats old, but they're my age or older, a lot of them. And they watch my stream because, you know, heck it. Life's too short. It's nice to put something on the background and maybe by osmosis learn something. 1,100? 1,100 hectopascals for 30 mils. Oh, we're getting to the end. Sorry, lab rats, for calling you all old. It's all ages. Fair enough, fair enough, fair enough. Just got in and already attacked. Okay, yeah, no, thank you, Soul Reaver, for chiming in. My community are experienced. Experienced. 25 mils is now... Oh, wow, look how far it went. Jesus, Mary and Joseph. 1,550 hectopascals. I think you guys are seeing a jump. Even though we're going down the same amount of mils by 5, the pressure gauge is jumping way, way, way higher each time. The last one now, it's physically hard to move this now. This is quite difficult to do. You're absolutely right, Kip. I even tried doing it before, but because this is not designed for hot air, I scalded myself, yeah. And there we go. 2,150. 2,150. Now, I'm going to see if I can do this. I'm going to turn off my Skyrim background music. I'm going to turn off the filter on my mic. So be careful, it's going to be quite grainy. And what we're going to do is turn up the gain. I'm going to speak softly so I don't burst your ears. I just want you maybe to hear the pressure pop. Don't do this at home. So, as you can imagine, there was a huge amount of pressure there. And when I released the pressure, it went whoosh outside. Don't do this because you'll damage your equipment over time, of course. But just for the sake of science, I did think it was important to show you. So, do you remember in spaceship movies? They would do that. They would, there's really, really high pressure inside the spaceship, just 1 atmosphere pressure. And then when there's a hole in the spaceship, suddenly all the air just whooshes out. So that's exactly what happened. And this is in that case, it's an explosion that occurs. I'm saying that carefully because if you're in a submarine, it's high pressure outside, low pressure on the inside of the submarine. So when the pressure faults, it implodes. It blows into itself like that. Right, let me pick you up, chat. Let me give you some upsies. Oh my god, so many accidents happened due to that, and I unfortunately know all too well because don't drop us. Because one time I was teaching about diving physics. Actually, I can talk a little bit about diving and explain the bends using everything we just studied today, chat. I'll do that in a second. But I was really interested in the diving story, and Medjay in the chat sent me a link to one diving incident. I watched like 40 recommended diving video accidents, and yeah. Thanks, Jay. I still remember that. I still remember that, Jay. Yeah, so let me explain the bends. Before we plot our experiment, and I'll show you the results and we'll prove Boyle's law. A quick thing to kind of mention is everything that we studied about the ideal gas law can be studied about our gas molecules in our blood. Surely we are aware that, you know, we pump oxygen around our body. Our heart needs oxygen. It pumps the blood around our body. Hopefully, that's the bread and butter. Root Fury, thank you so much for your Prime. Really appreciate that. Thank you. You're very, very kind. So, let's think about what happens to a poor diver. Poor crather, as we call him in Irish. So the poor crather has his suit. He's, you know, ready to dive, and he goes underwater. Whee! Boom. Okay? Oh, I'm not even going to talk about holding the breath stuff. Not even that. I'm just going to talk about what's happening in your bloodstream. Okay? I don't know why I show my hands. So when you're diving down underneath, I'm trying not to look at chat because you guys are very distracting. Sorry. Let me try and focus here. When you're diving in, think about what we just studied about Boyle's Law, Gay-Lussac's Law, and Charles' Law. So now you're diving in under the water. The pressure doubles every 10 meters. You're down. Okay, not every 10 meters, but it's 1 atmospheric pressure. That's crazy. Might not be very familiar yet, and we'll cover it a little bit later when we do some graphing. That's a lot of pressure on the body. Every 10 meters, another atmosphere. Another 10 meters, another atmosphere, approximately. It's a lot. So what is happening to your body? Think about it. If the pressure is increasing, if the pressure is increasing of the gas molecules inside of your body, what's happening to the volume? They're decreasing. Okay, so the volume of your gas particles are decreasing with increasing pressure. So as you're diving in under and under, you're having a great time with the fishies and the stingrays and the sharks and all that. Another law that comes into effect, it's kind of based on everything that we studied, but it's called Henry's Law, where as the volume decreases, or is it the pressure that increases, the concentration increases as well, which means that the particles cluster together more, the air particles, okay? So the concentration increases. The amount of gas particles in your system, so the amount of gas particles in your bloodstream are increasing. So as you're diving more and more further, first of all, the volume is decreasing, so the amount of oxygen molecules is increasing. So you're having a good time with the fishies, and then you decide it's dinner time, and you're just going to flow up to the top. And so you kick off from the stones or whatever, the seabed, and you're swimming to the top. Hold on a second. You've just absorbed a shit ton more of oxygen into your system now, gas molecules, and the volume is decreasing. Boyle's Law is happening now. Pressure is decreasing, volume is increasing, but you have a high concentration of oxygen as well. So not only is the oxygen molecules increasing in size, the ones that are in your bloodstream, but because you have so much more in your bloodstream, they coalesce to create air bubbles. And you might think, okay, so what? Air bubbles in your bloodstream is very, very bad. Maybe you heard of the story of very cruel murders committed to children. There was in stories. And the way they murder people in this way is by, exactly, a needle of air. By putting a syringe into a baby and just putting air in. Kill them. This is extremely dangerous. And this is what we call the bends. It is when it looks like The Exorcist, or the Exorcist? Yeah, a scene from The Exorcist when these divers surface up because they didn't allow the oxygen sizes, the volume of the air in their body to equilibrate. And so it gets into their bloodstreams, it gets into their organs specifically. There's a bit more story to that. A certain part of your body holds oxygen longer than other parts. And so it causes the bends. They go into these cruel positions that looks like they're being tortured or possessed by a demon, and it's very, very painful, and they can die. So that is how the bends occurs after studying all of Boyle's Law and Charles' Law and Gay-Lussac's Law that we just studied there. So that's just a brief summary. There's a lot more details about it, and a few people saying that they're divers in there. But yeah, exactly. So do you know when you have a syringe, and this is not a syringe, this is a board marker, and they have syringe, whatever they're going to give you, a shot or an injection or something. You know, they do this. It's to get rid of the bubbles. I work with vanadium flow batteries. That's my research. It's a type of battery that is, well, it's in the name, it flows. And so when we design the battery, we literally pick up tubes and we go like this all the time to flick the bubbles out. It's a great way of getting it to work. Hi, Yuli, welcome in. Welcome in, everyone. Decompression sickness, exactly. Yes, you do have oxygen, but remember, it increases the amount that you absorb and the volume change as well. So that's what causes it. You have so much more oxygen in your body than usual, and then the volume increases, and so they coalesce to create air bubbles, which is bad. Air bubbles is bad in your body. You'd think that's okay, but it's not. Oh, well, the idea, you flick the tubes, and it should work from here on in, because once that happens, you shouldn't have air getting back into your system. I say should. Obviously, anything can happen. But generally speaking, you won't have an air bubble happening again. Bubble physics, exactly. Okay, so what I'm going to do is I'm going to take a quick break. We have pre-rolls on, which means anyone coming in is getting ads. I'm so sorry about that. So I'm going to run a bunch of ads. We're going to get rid of them. I'm going to go to the bathroom. I'm going to pee. I'm going to pet my rabbit. She comes in sometimes. Maybe she'll pop in today. She's kind of grumpy these days. Just nasty, funny, too spoiled. But, you know, I'll still spoil her. I'll go and give her a treat. And yeah, I'll make a cup of tea maybe, a cup of coffee. And we'll come back and we're going to analyze the data. I'll just show you what it looks like. I'll go into my programming overlay. Oh, there you go, it shows. So this was the data. For anyone coming in, if you want to do this yourself, I might leave it on this overlay. And you guys are welcome to maybe put this into your own Excel. Okay? I'll be back in a little while. See you. Sorry. Hello. I came back. Oh, the ads aren't even finished yet. Wow, I flew through that. I put coffee on the stove, so I do need to grab that real quick. Okay, so while we're waiting for my coffee, let's analyze this data. So the first part I want to show you is that we can show Boyle's Law. I had a foggy brain moment there. I used the numbers to calculate 180. Can you actually? I suppose it's by extraction, no? Can you? Welcome back. Thank you, thank you. So anyone coming in, we just did the Boyle's Law experiment using our Boyle's Law apparatus. Bad boy here. Let me turn off the temperature sensor. Bonds, is that you? Heard things moving. Oh, that's Bambi, yeah. So, we said that pressure is inversely proportional to volume. So what happens if we just plot these two guys together? Let's do that. Insert, scatter, maybe a linear thing. Ah, that's kind of a weird graph. It's not a straight line, clearly. It's kind of like sloping like that. That's the inverse relationship there. Yeah, it's a bit odd indeed. What if I did that? What if I inversed it? Let's have a look. So it'll be 1 over V, basically. So per milliliter. Hi, Buns. How are you doing, sweetie? To the -1. I'll show chat our bunny. Ta-da! This is Bambi. She's our overlord. Anything she says goes. If she thumps you, work harder. This is the message Bambi wants to send. Oh no, I won't do it on the front page. That's her little house out of my bamboo AMS box. I did buy bananas. We will give her bananas in a little bit. Yeah, that's our bunny. That's our bunny. Kind of in a bad mood 2 days with me. I'm not sure why. I didn't really do anything. Destroyer of boxes, thumper of chat. Excellent, excellent, Delara. And yeah, we have a little emote created by Jay as well. I think it's in my ad overlay. I prepared it.
30 degrees makes the maths a little bit easier. Resolving these vectors.
This is just my ad thing, and I have a little Bambi there in a little
Component
hat.
is 39 meters.
Medjay created all of that. Amazing work. Okay, here we go. Let's go. So what I'm going to do is I'm literally going to make Excel do all the work. I'm what we like to call a lazy fecker. So what we're going to do is we're going to put, quite literally invert it. We'll say 1 all over this number. There we go. So that unit now is per milliliter. So let's see what we get if I graph those. Because we said that they were directly proportional to the inverse. That means, lo and behold, a lovely straight line through our graph. Voila. Means it's directly proportional. Our data looks really good, doesn't it? That's a really nice straight line. I know that a lot of people who do Excel stuff will say, oh, how good of an R squared value is it? And I hate talking about the R squared value because the R squared value is actually quite complicated. And my argument is always, if you don't know how to use that R squared value or what it means, don't use it as an argument. So it's just a thing of doing any presentations, any lecturing, any talks. If you don't truly know what it is, it shouldn't be up there. Basically, this is an isothermal process at the time as the Yes, exactly, Druv, exactly. I actually just released a YouTube video on the isothermal process. If anyone's interested, I upload like short YouTube videos. Not shorts, but I do upload shorts as well. But they're short physics videos. And if you guys are interested, literally yesterday, last night, I did the compression work of a gas. It's like 6 minutes long. It's posted here in the chat. There you go, guys. It's 6 minutes long, and it's talking about the compression of gas, and like you mentioned, isothermal and adiabatic processes I mentioned. Jotello, thank you so much for your prime. Really, really appreciate it. Thank you. You're very, very kind giving me your prime. All the money goes to feeding this little evil bunzo. I just discovered the channel, so I'm glad. That's the beauty of the front page. Like, being thrown in, because like before I started teaching physics, I didn't know that there was a single science communicator here. You know, I was just playing games like any other person. And it's so cool to think, oh, people do this kind of stuff on the internet. I don't know. I think it's cool. If you guys find anyone else who does this stuff, let me know. I do a thing called Tofu Tech Talk. I haven't done it in a while because I've messaged so many people and everyone's like, yeah, I'd love to be interviewed for a podcast. But we haven't scheduled anything, and what's going to happen is in a second, everything's going to crash over. Okay, this isn't good enough. So we've shown, we have shown that Boyle's law is true. Pressure is directly proportional to the inverse of volume. We're going to go one step further, ladies and gentlemen. Lab rats and labradoodles and everything in between. What we're going to do is we're going to calculate the amount of molecules that I had trapped inside this gas. I'm going to sit down and we're going to count every single molecule in here. Every single one of them. But we're not going to sit and count them. We're going to use our big brains and we're going to actually do maths. And here's how we're going to do it. We'll take, yeah, it might take some time to count them, but we'll do some maths. There's a couple of things we need to do to fix all of this mess. Okay? First of all, hectopascal. Who's that? Oh, my coffee's almost ready. Let's change the gauge pressure. No, how do I do lowercase g's? Oh, Jesus. I don't know how to do it. Gauge, we'll say P gauge in units Pascal. Gauge is because this guy here. This is what a gauge meter, gauge meter? Just a gauge is. It's reading what the pressure of the internal part is relative to atmosphere. We'll talk about that in a second. I'll be right back. Oh, so you're as insane as me then, Jet. Anytime I mention that thermodynamics is my favorite, I get shunned. Okay, chat, I want you to babysit the bunny. Keep an eye on her. I'm making my coffee. Chat. Keep an eye on the bunny. Don't let her eat my PC.
Commander, set a new course. There's coffee in that nebula.
Heard that. I'm gonna give Bambi a little watermelon. The watermelon is way too sugary, so only a tiny, tiny piece, and very rarely, in case anyone has bunnies, very rarely are you allowed to give it to them. Oh. Oh, it's a good watermelon. She does this little thing where her butt twitches. Wow, what a lovely mug you have there. Thank you, Yuli. Thank you. Happy Saint Paddy. It's Saint Paddy's. Patty is a nickname for Patricia in Ireland, or you know, for most of the world. Paddy is for Patrick. So many potential lab rats. There are a lot more new victims. So again, guys, if you support this channel, you automatically become a lab rat. And if you automatically become a lab rat, you guys, you know, will be signed up for experiments and digging in the mines. Just be careful, don't summon Balrog, of course, but or do. Okay, so let's talk about the gauge pressure. Gauge pressure is the pressure that was read on the gauge part. Do lab rats get watermelon too? Listen here, Vari, do you think I'm made out of money? Do you know how... I was going to say, do you know how much money lecturers get? Okay, hecto means by 100, right? So we're going to grab this number and we're going to multiply by 100 to get it in pascals. And let's drag it then. Whee! Whoa! That's okay. So you can double check that we did it correctly. We'll click on one of the cells and it says that it took this number and multiplied by 100. There we go. Oh, spinach, I wish. I don't know what the conversion of the Australian dollar is roughly, actually. Let me look at that. What is one Australian dollar? Oh, no. Oh, God, no. No, no, yeah. I wish. I take my statement. I wish. Okay, here we go. Is it P-gauge or P-gauge? Pressure gauge, pressure gauge. Pagage, there we go, Vog, pagage. Now, the next thing we're going to do is we need to add something to that. That's not the true pressure, chat. It's all a lie. That's not the true pressure that's inside that gas canister, that syringe. Do we know what we're missing from that? It's gauge, is that, yeah. Oh my God. I thought you guys were just making fun of me. Anyways, go on. I'll go back to it. Atmospheric pressure, exactly, not so fast. That's just what is inside the canister without the pressure of the atmosphere. So the pressure of the atmosphere roughly is 101,000 pascals. But depending on the weather, it changes. This is an actual thing. Maybe you guys have seen the news and they'll show in the news these lines being drawn, like, and it goes from blue to red. There's temperature kind of pressure lines. Isobars, thank you, Zier. But sometimes there's pressure. So the change in pressure affects the weather. And so all these barometers and so on and so forth can predict the weather that comes in. They're not very good at it. Metrology is a bit weird, but yeah. What did I want to type in? What is the pressure in Ireland today? What is atmospheric pressure today? So I don't know if you guys can see, it's very overcast today in Ireland. It's actually pissing rain, as always on St. Paddy's Day in Ireland today. Oh, it's quite low. Huh? Yeah, it's a bit low today. It is 100,200 pascals. Okay, that's what it is today. So we'll say today's pressure in Ireland is 100,200 pascals. So usually it's about 101. Thanks, Dumpster. What are you talking about today? Welcome in, everyone. So what we're doing today is that we did an experiment talking about Irish physicists, and we talked about Boyle, and we did Boyle's law experiment. And right now we're going to measure how many gas molecules were trapped in this canister. Bunch of maths in Excel to show you how it works. And after that, we will continue with our next scientist. I believe is Stony. Buns. Well, We're on the front page today, so be nice. Be nice, okay? Hello, everyone. This is Bambi. She's a rescue bunny that we got about a year ago. She's a little bit of an old lady now. She's past her midlife crisis. She's grumpy, and she's, you know, knows what she wants and doesn't want, and she thumps me every day. And she hates it when I pick her up and kiss her. Actually, she likes kisses. An old bunny for an old lady streamer, exactly. She has the tiniest ears. She's the cutest bun in the world. Mwah. So she's free roam, which means that she can just run around the house freely. We do close most of the doors in the house at night, but yeah, she's allowed in this room, and we have a little cutout cardboard for her to hang out in. I don't bother buying her nice stuff anymore. She doesn't like the fancy stuff. She likes the cardboard. It's the cardboard. She loves the cardboard. Yeah, cables. Oh, she eats the cables. We have to be careful with that. The amount of cables she's eaten in this house is just shocking. Shocking, pun intended. Okay, so what we're going to do now is P absolute in pascals as well. Pascal is the SI unit for pressure. So we're going to grab this number and we're going to add it to this. Now, in case you guys didn't know in Excel, if you didn't want the figure to drag and keep constant, you put a $sign before the B and after the B. In this case, it traps the column and the cell in total, if that makes sense. Thank you so much for your Prime, Snap. Really appreciate that. Welcome in, welcome in. You've joined willingly, I'd like to highlight. Do you have an estimate when Bambi completes her PhD? I don't know. She's a procrastinator through and through. Just like her mother. Hi, Logitech Gal. Welcome in, welcome in. Oh, sorry, I hit the mic. We have fixed pressure. Woo! Pressure is done. This is the actual figures that we are going to plot, and we are going to get the right answer. Teamwork. Yeah! Now let's look at volume. Okay, chat. First of all, it's in milliliters. The SI unit for volume is meters cubed. How many milliliters are in a meter? This always trips people up. It's weird because it's not a normal unit. Too many. So here's a quick way of thinking about it. The first step is how many milliliters is it in meters cubed, right? Because a liter and a meter are two different things. Exactly. So what is 1 milliliter? 1 milliliter is 1 centimeter cubed. 1 centimeter cubed. Okay. So if I wanted centimeter is, there's 100 centimeters in 1 meter. And, oh, I have a meter stick in fact today. Meter sticks. Nope. I always do this as a visual demonstration. It's really, really nice to kind of, whoa, sorry, wrong overlay. So this is what 1 meter looks like. Grab another guy like this. Oh, Jesus. Can't even fit it into the frame. Oh, that's 1 square. And then the depth of 1 meter again, that is 1 meter cubed. It's a massive volume. So what we're going to do is think about what each one we're multiplying by. So how many centimeters in a meter? 100. So it's 1 dimension by 100. 2 dimensions by another 100. 3 dimensions by another 100. It's 100 multiplied by 100 multiplied by 100. 1 million. So it is 1 million centimeters cubed in 1 meter cubed. That's a lot. I know. It's quite shocking to think about it. But in 1 meter cubed, there's 1 million centimeters cubed. Do you see how big my box was? Here's a quick rough estimate for you. There's 1,000 centimeters cubed in 1 liter of milk. Do you know your little 1 litre of milk that you buy in the store? In Ireland, anyway, that's very typical. Oh! Bones, I got scared too. Jesus. You okay? Oh. My goodness. A little thing fell over. Whew. That scared me too. Okay, it's okay. Right there. Anyways. So 1,000 of those litres of milk will fit into 1 metre cubed. So that's a lot of litres of milk that fit in there. They can hiss, yeah, but that wasn't a hiss. The fence, I have a little metal gate here that we tried to build outside, and I just put it inside and it fell over. It scared me and Bunzo. Got startled. Oh, good. I'd love to live in a bamboo lab, AMS. That's right. That's right. That is a ton of milk. It's a shit ton of milk. 1,000 litres of milk will fit into 1 meters cubed. It's quite crazy. Like when you first encounter volume and SI, it's insane. Okay, back to the actual calculations. So what do we need to do? We need to grab this guy and we need to divide it by 1,000,000. 1, 0, 0, 0, 0, 0, 0. There we go. Drag it down. And voila. All right. So we have converted volume into meters cubed. What do we need to do though? We need to invert it because it's an inverse of volume. Remember that? So it'd be 1 over V, which is 1 over meters cubed, the inverse. There we go. So we grab this guy, 1 divided by this guy, and we drag it down, and voila. Ta-da! We have converted everything in SI because, chat, every single one of you, and I say this all the time, and I do mean it, every single one of you, mostly, in some shape, way, or form, is a physicist. Because Boyle said that pressure is directly proportional to the inverse of volume. That's why it's the inverse. That's what Boyle predicted. And we'll plot these two guys, and let's see what we get. Oh, do I want... we'll see which way we do it. We'll put this into a scatter. Oh! I'm clutching my pearls. Look at how beautiful that is. And so we have pressure on the x-axis and volume on the y. Do I want that? You know what? I'm going to do a quick thing. I'm just going to put pressure again on this side, just because I think... It's just the numbers. I think I want pressure on... Yeah, I think I want pressure on the y-axis. Yeah. I did nothing. I'm just switching which one is where. It's just easier because I'm going to show you the maths now. So, like any good student and any good scientist, we have to label everything. This is the ideal gas law. This is pressure. Absolute pressure. In brackets, always the unit. Do not forget your unit, chat. You will lose marks for that. And here is 1 over volume, and in brackets, m to the power of minus 3. Okay. Let's add a trend line. It's a best fit line and display the equation of the line. Voila. Well done, team. Well done. Now, unfortunately, buckle your seatbelts and we're going to go back to the whiteboard because now we have to do maths. No, inverted volume. Don't think about it from a actual thing. What we're doing is a mathematical thing. It's a number, like number 2. If you invert number 2, it becomes 1 over 2, which is just a half. We're just doing something to the number, if that makes sense. Not necessarily to the physical parameter of it. All right, let me pick you up, chat. We're going to go to the whiteboard. Time for upsies. Have the Skyrim music playing. Okay. Oh, you don't see the better. Perfect. All right. Let me increase the volume a bit. I'm afraid of maths. Don't worry. I'll hold your hand. We're going to hold each other's hands through this. Isn't that right, Buns? She heard her name. She flicked me off. Where's my marker? Here we go. So, what we ended up doing is we ended up plotting pressure versus 1 over V. We got a straight line through the graph, and the equation of the line that we got was y is equal to 6.27, we'll round it up, 2.8 x plus 3055.8. Okay, so that is the equation of the line that we just got. Now, remember the ideal gas law. The ideal gas law said that pressure times volume is equal to nRT. Let's rearrange this equation. P is equal to nRT times 1 over V. If V is being multiplied over here, when we bring it across, it's going to be divided. And that's exactly what we just plotted, chat. Hold on a second. Hold your horses. We plotted this here on the y-axis. We plotted this on the x-axis. And if you guys remember your equation of the line, it's y is equal to mx plus c. Some people use a and b, it's fine. The letter doesn't matter. It means that what you plot on the y and what you plot on the x, the slope of the line m is the number in front of the x. And the intercept is a constant. We can match all of this. We don't have an intercept here. It's just 0. There shouldn't be an intercept, but no physics experiment is perfect, so that's okay. So what is remaining is this guy. This guy says that the slope m is equal to nRT. Chat, do you remember what the temperature was while we were doing this experiment? It was 20 degrees Celsius. Excellent. Temperature is equal to 20 degrees Celsius. What did I say? It was about 19.9 to 21. It was to 20.1. So we'll say 20 degrees. That's not good enough. Thank you very much. 293.15 Kelvin. To convert it to Kelvin, we add 273.15 to it. Exactly, we want it in Kelvin. Well done. Because Kelvin... Why are you Oh my god, you can't keep thumping me. Did chat hear her thump me? Thumping about? Oh! Did you guys hear her thump? That was my bunny thumping me. She doesn't like Lord Kelvin. I mean, he got his lordship because he didn't support home rule. And we're talking about it on St. Paddy's Day. Do you know what? Bunzo is an Irish bunny through and through, clearly. Clearly. She doesn't like Lord Kelvin. A very, very proper bunny. Irish bunny indeed. Okay, where was I? We have to use Kelvin because it's the only one that has an absolute 0. There's another unit, but we don't tend to use it. It's a very ancient unit. We won't mention. And so that is what our temperature is going to be. R is the ideal gas constant, and it's just a number. It's an energy constant. Is it 8.13? I need someone to look it up for me. I don't remember on top of my head. Ideal gas constant. And watch the unit, because the chemists don't use the right volume. They use liters, so watch out for the unit. 8.314. There we go. Mole per Kelvin. Yeah, so you'll see it if you Google it. It'll give you 2 different units, so be careful about that. 8.314. Those damn chemists. So, from this graph then, it means that we could calculate n, the number of moles in our particle. Let's do that. Let's clean up this board here. Actually, we have space. Let's continue the maths. I'll grab another color marker. Oh no. It's just if I use green or red, you won't see it properly in the lighting. So I'll just stick to this, okay? So what we're going to do is the slope is equal to nRT, number of moles, ideal gas constant temperature. We're looking for this guy. Slope divided by RT. The slope was, let's check our Excel graph. The slope said it is 6.2795. All divided by 8.31. 8.314 and 293.15 Kelvin. 314. Oh, that's just pi. Okay, I should remember that. And T is 293.15 Kelvin. There we go. Okay, chat. I want you to grab your calculators. Where's mine? Okay, it's in my school bag. What do we have here? It is 6.2795 divided by 8.314 in brackets multiplied by 293.15 and we close brackets and we get a very, very small number, and that's okay. That's good. We get 2.576 by 10 to the minus 3 moles. We don't even have a mole. We have a very, very small fraction of a mole. Ah, fair enough, Spectral. Welcome in, welcome in. You guys are all more than welcome here. Loads of new people. And I know that you're jumping in the middle of a lesson, and do not fret. We will, there's 4 lessons in this class, if that makes sense. So whenever you're jumping in, you can stick around until the next lesson. So the next lesson we're going to talk about is Stony. We're going to talk about the atom, and we're going to talk about Coulomb's law, the electric field, and the potential. So that'll be our next lesson. But we're almost done in this part here. Got a message asking if I wanted a St. Patrick's Day treat. Okay. That's not the amount of molecules though, is it? So what? I know that there's 2.576 by 10 to the minus 3 moles. So what? So what we're going to do is we're going to go back to our good old friend that put the ideal gas law together. We're going to go back to Avogadro. The cool thing about Avogadro is we share the same birthday, so and he was an introvert. The poor creator did so much work in this realm. But because he was such an introvert and he was a physicist, the chemists kind of shunned his notation and they didn't want to study it. So they were kind of like, No, this is all physics. This is all physics. Chemists do use the term moles, but it did come from a physicist and it is used in physics. It's all just physics. Chemistry is just a sub-branch of physics. Where tea is equal to toast. That's probably the issue with AI, unfortunately, Lazy, yeah. Okay. Can an introvert become a teacher? Yes. Oh, absolutely. Most physicists are all introverts, in my experience meeting them. But lecturing is unique. doing presentations and lecturing isn't necessarily... Yeah, because what an introvert is a person who gets drained of energy by communicating with humans. When you lecture and teach, it's not really social. I know this sounds weird, but I don't when I lecture and teach my students, I don't consider it a social interaction. The social interaction is chatting with your students afterwards. That's the social interaction. When you teach, yeah, I very much dissociate. It's a different thing, I would say. Yeah. I can jump in and chime in to say that I myself am an introvert, and it's very, very different. And the reason why I can, there's no chance in hell I would be this confident in front of really 5,000 people. But the 5,000 viewers we have at the moment is just it's just a number on the screen. It doesn't mean anything. Chat, stop it, stop it. It is still a very different skill set to be able to stream and then teach in a real lecture as well. We're imaginary, chat. You are imaginary. You have J's and I's after you. But the good news is, if you guys find another imaginary person in your community and you square each other out, you just become -1. Have fun with that. Right. So, we learned that the amount of moles that we have is 2.576. 2.576 by 10 to the 10 to the minus. So we have a very, 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 very small fraction of the amount of moles that we have. We don't even have one. It's only a tiny fraction of it. Now, how do I get the amount of molecules present? Well, Avogadro said, not avocado. He said that in 1 mole of a substance, there's 6.022 by 10 to the power of 23 molecules. That means that if I had 2 moles, if this number was actually just 2 on its own, I would get 6.022 by 10 to the power of 23, multiply it by 2, and I would get 1.2 by 10 to the power of 24. No, do not confuse with the moles in your garden. But also, you have moles in your garden? That doesn't sound good. They sound like bad things to have in your garden. Anyways. So what we're going to do is we're going to grab how many moles we have, and we're going to multiply by this constant. And we should get how many molecules are present in our system. How many molecules did I trap inside of this container? So I'll zoom in here. How many guys were trapped just from here to here? Yeah, we increased the pressure and the volume. Yeah, we did all these kind of things. But how many molecules were there? So you're going to grab your calculators. I just got insulted and yelled at, but I like it. Reminds me of 6 by 10 to the minus 3. All multiply by 6.022 by 10 to the power of 23. We got 1.55 by 10 to the power of... You don't have a scientific calculator, Tetsu. Your Talvion, thank you so much for your prime. You're so kind. Thank you so much for supporting this channel. .55 by 10 to the power of 21 molecules. That's how many... Chat, how many millions is that? What is that? That is 3 times a million, at least. I think I'm keeping track of the zeros. That's how many molecules are inside here. Just right here. Just from here to here. That's all. That's all there is. There's billions and billions of molecules trapped inside. That's insane. We did it from 65 mils to 20 mils, Kip, but because we plotted pressure versus volume, the amount of molecules remained constant because we sealed the gas canister. There was no way molecules could get in, but we changed the pressure and volume. You count them to verify? It's 1.5 by 10 to the power 15 million. Yeah, yeah. That's a lot of molecules. It's a lot of molecules. So I'm going to just sit down for a few minutes, if that's okay with you, lab rats. Let me do some picky uppies. Upsies. Let tofu pick you up. I'm just going to take a little break of standing before we cover our next topic. We've completed one scientist today, which is Robert Boyle from County Waterford. This is Twitch, yes, last Pokemon. So yeah, in case you guys are wondering, I also play games as well. I teach physics and I do projects for anyone coming in. Welcome in. I have loads of stuff. This is my lab. Welcome in. I'll do a little quick tour to take a break between the scientists that we're talking about today. We finished Robert Boyle. Robert Boyle is done. We've done County Waterford. We've done Robert Boyle. And we're going to move in time. And the next guy we're going to talk about is Stoney. If you check the title, we're also going to talk about Walton and Longsdale. So those are the scientists we're going to talk about. But a tour of my lab! And where a lot of the sacrifices are made. Behind the chat box is a CNC machine. Here's a 3D printer. It's freaking not working lately and I'm getting a new one. I have a shelf full of robots. Chat, don't judge me, don't judge me. But Cricket went through the mines. I know. Look what happened to Cricket. I will repair Cricket. This is Jeremy. He's our skull that we talk to. We get a lot of advice from Jeremy. Jeremy's lovely. And this is our demon core that I tried to fix, but one of the wires is loose, so I need to fix it. I'm going to bring it into university this week because I'm doing a demo for some of my students this week, so I need to bring it into work and make sure it's working. No, it's just a 3D printed skull. I have this idea. So over the summer, I'm going to paint the walls in this house. Jeremy, her first husband. I'm going to have this idea of, so this is a 3D printed Tyrannosaurus Rex skull. I'm going to paint black holes on my walls, and I'm going to have skulls coming out of them. I don't know why I'm doing this. I thought it was cool. I haven't seen anyone do it. I don't know where I got this idea from, but I thought it was really, really cool, and that's my plan. Rawr. So other stuff that we have in our lab is this, guys. These are vanadium electrolyte. This is vanadium 4 and this is vanadium 5. If anyone's wondering what vanadium is, it's an element and it's what I research. I study a particular type of battery called a vanadium flow battery. And I think it's in my PhD command, is it? I haven't updated that in a while. Yes. Now I'm just a full-time lecturer. I started last year or so, doing extremely well in my career, and now I'm starting, hopefully soon, my own research group. I have my first student doing work at the moment. So yes, my research group has begun. What is on the left of the 3D printer? That's a CNC milling machine. It's the opposite of a 3D printer. It's a drill bit inside, and it drills things out for you. So this is what it did. You put in, this is epoxy. You put it in, and it carves it out for you. So instead of printing it in, it carves it out. Hi, Jamie. Good morning. Exactly, systems. Systems administrator explaining that is a perfect username for that. So yeah, I was sponsored by Makera. I'm not sponsored by them anymore, so take what you will. It's a really nice CNC milling machine. If you're into that kind of stuff, it's user friendly. I'll highlight that CNC is harder than 3D printing before anyone thinks it's the same thing. Yes, they both use G-code, but it's not as simple. It is a little bit more complicated, but it is cool. It is very cool. Oh, I plan to do a whole bunch of series on it, Druv. I just started doing that on YouTube. my thermodynamics series. My first law of thermodynamics did extremely well. I really, really hope I get monetized on YouTube. It would really, really help. But yeah, I uploaded that thermodynamics compression of work last night. Hopefully it does well as well. Regardless, yeah. Crashing a CNC is equal to fun. Anyways, ultimately, that's what we do on stream. I build projects. At the moment, the project that we're working on is... Where's my project? I'll show you what my project is. Our next project that I rage quit recently because my programming skills are null is this guy. Okay, so I have an infrared sensor and a PIR sensor here. I'm building a real tricorder. So I need to build the electronics first and programming everything. So I have 2 OLED screens in here. One would display fluctuations in temperature and predict if the body that we're focusing on is possibly humanoid. And this guy is a PIR sensor, which detects motion. So if there's something hidden in the walls and it's moving, this guy will detect it and confirm whether or not it is a life form. So the last thing I need to do is I need to come up with another sensor, tricorder, 3 things. I don't know what the next one is. There was a conductive idea that we had a while ago. Some of my wires are coming out now. I need to fix this. I hope I drew a diagram. You know, I hope I left comments in my program. Oh yeah, sorry, it's from Star Trek. It's from Star Trek. We tend to love Star Trek here. We have a few Star Trek commands, and if anyone raids us, it's very early in the morning. I don't think any one of our friends is raiding. This is what happens when someone raids us.
Red alert. All hands stand to battle stations. Lay in an intercept course to the Romulan ship.
Shields up. Load all torpedo bays. Stand by phasers.
Warp factor 8. Engage.
And obviously a few sound commands as well. So yeah, big fans of Star Trek. So if someone raids us, we'll have to do that. I try use it with people who are coming in from communities I know, because sometimes it can seem a bit aggressive if it's a new person. So if in case anyone's wondering, she didn't do it for everyone. It's like, yeah, if it's a new person, we might be careful with it. There's probably not any comments in the code. Yeah, no, I'm very, very bad. So the next 3 scientists we're going to cover is Stoney. So we're going to talk about the electron. Then we're going to talk about Walton, splitting the atom. We're going to do a bunch of maths now. And in the end, we're going to talk about Kathleen Longsdale. And even though she was in chemistry, she was using a very classical physics thing, X-ray diffraction. And I have a big box of everything we need. We're going to have lasers. We're going to have an X-ray diffraction. I'm going to hang up some pieces of paper, maybe over here so you guys can see it. And we're going to show how people using X-ray diffraction can measure the size of atoms. It's a really, really cool physics thing, and I really want to show it to you. It's not exactly X-ray diffraction before anyone, says, oh, she's going to use X-rays live on stream, cancel her on Twitch. I'm showing it using laser diffraction, but it's the same principle with X-ray diffraction. I read that CERN has achieved being able to handle an antiproton. I don't know about the symmetry. If you're talking about supersymmetry, as far as I know, most particle physicists aren't supporting it anymore. Could be wrong. They want supersymmetry. Physicists love symmetry, but I don't think it's possible from here on in. That being said, I'm not a particle physicist, Dark. I'm a classist. That sounds bad. So bear in mind that my opinion means absolutely nada. Absolutely nada. King Anna, welcome in. But absolutely, 6563, take care of yourself if you need to work. Okay. What time is it? Don't save. Turn off Excel here. Do we have background music? We do. I have a study Skyrim music in the background. to set the mood. Okay, we'll close all of those windows. We have so many, you know. Should I open my lecture notes for this? I have lecture notes. I might boot up my laptop if that's okay. Just so I have some reference points. I can teach this on the wing, I think, but it might be nice to know. That I don't deteriorate too much. But yeah, I teach physics. Sometimes I build robots. Sometimes, and sometimes I video games. So that's usually. We're playing Dyson Sphere program at the moment. If I finish this lesson too early, I might play some Dyson Sphere, but I have a fear of three-dimensional space, and I realized in my last stream that there's three-dimensional space issues. Yes, yes. What do you mean what happened to my podcast? I'm inviting people. They said they'll get back to me, and they're not getting back to me. There's only so much I can do. I'm messaging people, but I'm running out of podcast victims. You know what? I didn't realize how much of a niche this was, finding scientists on Twitch. It's quite hard. How often do you stream? Only twice a week, on Saturdays and Sundays at best. So today, the only reason I'm able to stream on Tuesday is because it's St. Patrick's Day. It's a bank holiday in Ireland. So it's my day off, and that's the only reason I'm able to stream. But at best, I only stream twice a week. I unfortunately have to work full time. And I do a lot of other stuff on social media. If you guys want to check out my Instagram and stuff, I post a lot of different stuff on it. Like problems and derivations and solutions to exam papers and so on and so forth, if that's what you're into. If you're like taking a degree in engineering or science, I might be a bit more help of you there. Here on Twitch, we tend to do a bit more fun stuff. What's this thing? Electrostatics. There we go. Just pulling up my lecture notes on this. Just so I have a structure for this. I teach the history. You know what? I'm going to teach the history. It's fun. History is fun. Why do all science and tech streamers have so little time? Well, here's the thing, right? If I were a full-time streamer, I would stream 5 days a week, right? But I think it's kind of, what's the word? The reason that you guys watch me is because I can build things, is because I teach this, is because I'm in science and I do research. And you're coming into the stream and you're learning something from me, right? But if I were to quit that and do this full time, I don't do that anymore. Does that make sense? So I don't have that, connection anymore. So then the reason that you would follow and support me is gone, if that makes sense. So me going full time is kind of, yeah, counterproductive. We also stream more in school holidays. That's true. During the summer, I stream a lot more. Summer is going to come out soon. Do you give insight into the use of AI from a professor side? Look, it's up to every lecturer to control AI usage. Because I teach physics, most of my examination process is exams. So I don't have to worry about AI too much. The only thing is worksheets, or not worksheets, lab reports. And so what I've done is I've changed the style and the load of worksheets, where the report is heavily emphasizing calculations, tables, and descriptors, and, you know, explaining the calculations that they're doing rather than anything, and then reduce the weight on discussion slightly. So that's what I do to adjust for AI, because you can't accuse anyone of AI, honestly. Yeah. Which field do you stream? So I teach physics, I build electronics, and then I play games. So those are my three fields of fields that I stream in. The stream is AI. Yeah, full-time lecturer. Full-time lecturer, full-time researcher. In university, if you're a lecturer in STEM, I don't know if that's across the board, but if you're a lecturer, you're a researcher as well. Okay. So the hour is coming off, pre-rolls are about to go on, so we might run some ads. I might get a bottle of water, and when we come back, we're going to start a new topic, and we're going to start talking about Stoney. So Stoney is an Irish physicist, Stoney, who came up with the name electron. That's pretty much the only kind of major contribution he did. I know that sounds bad, but we'll talk a little bit about him. And thanks to him, we're going to talk about Coulomb's law, the electric field and electric potential, which will build on a very famous Irish physicist, Walton, who got the Nobel Prize for fission. It was the first mankind manual splitting of the atom. There we go. Got there eventually. That was really, really bad. But basically, it was the first time the atom split, and we're going to talk a little bit about nuclear physics. Exactly. So we're going to cover all of that on the board. So we'll get back in a little while. I'll see you guys there. I'm going to run some ads, and on my overlay, these are some videos from my own YouTube. If you guys want to check out my science YouTube, I really, really appreciate it. My watch hours are almost there. I'm almost there with the watch hours. But all of these videos are on YouTube if you guys want to check my coffee first. And as I'm getting my coffee, I do all my, like, you know, makeup, hair, all of that, getting dressed. And then the last thing I do before I leave to work is brush my teeth. But because streaming was work today, yeah, it was weird. Oh, I'm glad to hear that, Rentre. I'm glad to hear that you guys were interested in this. It is weird, like a lot of people wouldn't have known that physics exists. And I really am grateful to Twitch for the opportunity to be put on the front page, honestly. Like, yeah. Because, you know, discoverability is tough for many people, and you have to go off Twitch to find people. And I do, and it's great success. But obviously, you know. Teacher drinking in a plastic bottle? Yeah. Yeah, absolutely. Reduce, reuse, recycle. Not only am I a physics teacher, but I am a, what's the word? Environmentalist? Well, not really. But like, I definitely believe in the 3 principles: reduce, reuse, recycle. So we're reusing. And if you're not going to talk about microplastics to me, lads, that's the least of my worries these days. And mostly all classical. I don't do, for example, like electromag. Yeah. Yeah. Like, I actually think this might not be a good bottle to use. We've had this maybe for a lot longer than 365 days. There's also repurpose. Exactly. So we got the bamboo box from Bamboo Lab. And so we use that box for Bambi. Oh, check this out. You see this one? So this is my Steam Deck I got for Christmas. And Bambi loves it. And she eats it. And we put a bit of hay to let her munch as well on it. So reduce, reuse, recycle. Those are the 3 things I am a big fan of for sure. So, you know, if you guys are, you know, very big into battery technology as well, similar to me and all of that, and you want to buy a hybrid or a car like that, rather than buying a new car, just use your car, whatever it is, even if it's petrol, to the point until it's broken, right? Reduce, reuse, recycle. They're very, very important, that order. And just use up the car that you have, because creating a new car and putting it into the environment is very, very harmful. So reuse what you have, lads. Repair what you can. That's the best way. What we humble low, I was going to say low humans. What are we referred to as the people who are not millionaires and billionaires that are doing crazy stuff, and like political leaders who are just, you know, doing crazy stuff around the world? What are we called? Plebs. Thank you very much. We're just plebs. Exactly. That's what we are. That's all we can do. Peasants, broke. Yeah, no, you know what? That's all correct. That's exactly what we are, chat. So, yeah. Yeah. Okay, so I have a little notebook, just some written notes that I have. Serves. Okay. Now we're going to talk about George Stoney, and the representation from Ireland we are going to is Offaly, County Offaly. Now, County Offaly is class in Ireland because that's a lot of where my work is implemented. So this is the central part of Ireland where a lot of grid stabilization work is done. Really, really cool. So this is where battery technology integration is introduced, so that when a big generator shuts down suddenly, you need enough time, you need to buy enough time to respond to the electric grid. Because when a generator shuts down, right, the frequency, some of you guys have 50 hertz frequency being operated on your grid, some of you have 60, depending on which nation you're from. Usually the blanket statement is America versus Europe. I'm not too aware of other. Most countries in Africa are 50 hertz, I know that, because I worked with some stuff in Zambia and I did a bit of research in that. But anyways, that's a sidetrack. I'm not too sure about the rest of the world. Now, when a generator goes down, the frequency generation, the AC current, is going to decrease over time. And so what you can do is you can introduce a battery, a big ass battery, into the grid to respond to that very, very quickly, bring it up to 50 hertz, and it only operates for like 10 minutes. A lot of people have this misconception about electrochemical battery storage technology integrated with the grid, that they're going to be this big, big, giant battery so that they supply hundreds and thousands of megawatts of energy and they can run all night. No. So what they're really used for is for stability. They're only there to respond very, very quickly for the electric grid, ever so slightly, to buy you time to put another generator onto the grid. It could be a gas turbine, a coal one. We don't have any operational ones anymore. Maybe Money Point is still up. Or a wind turbine farm or a solar panel, whatever you need to integrate to the grid, it buys you time. So usually these batteries are placed to buy time. Sorry, that was a complete sidetrack. That wasn't even, part of the talk. Anyways, that's County Offaly for you. That's where a lot of the research and a lot of the industry work is being done. That's the cool county for it. The other thing in that county is Tullamore Dew. So if this is after all St. Patrick's Day. Tullamore Dew is an Irish whiskey. I hope it's a whiskey. I'm not too sure. But Tullamore Dew is their very, very famous whiskey. It's a Scotch, is it? I think it's whiskey. Scotch is Scottish, right? Anyways, there we go. Kind of quizzical, exactly. So, the scientist that we're going to talk about is George Stoney, and I don't know when his birthday is. I never write these things down. George Stoney, what century are we in? It must have been ever so slightly in the 1800s. So he was born in 1826 and died in 1911. So his research was done in the mid to late 1800s. So that's where we are in the timeline, roughly. And George Stoney, what he's famous for, and what he's famous for as an Irishman, is he coined the term electron. They knew about charges, okay? That was definitely a thing that they knew. So what happened historically is that when they discovered the capacitor and when they built the first voltaic pile, they discovered that charge was flowing. They didn't know if it was positive or negative at the time, but there was a flow of charge. And famously, Benjamin Franklin helped with a lot of the theory and the ideas at the time. But then Stoney came around and said, do you know what? I think there is a fundamental charge associated with it. There's a minimum value associated with it. And so what he thought was possible was he could measure it. So he tried to perform a whole bunch of electrolysis on it, tried to do a whole bunch of measurements, and he did associate the negative charge with the term electron. And it was a coined term that caught on very quickly. So what's funny about this is that Stoney was like, oh, I'm trendy. I set trends. Because once he said what electron was and when it was discovered, and we'll talk about J.J. Thomson in a second, Stoney thought, yes, this is going to be my thing as a physicist. I'm going to name things. And so the poor Crather decided, this is a bit of an exaggeration, but bear with me. He decided that he wanted to introduce a unit in physics. And it was this cross-dimensional unit. It was a base kind of unit. Where was it? It was basically a unit of natural units. There we go. And he wanted them to be called Stoney units. He wanted to name all natural units on the basis of another unit called the Stoney unit. Humble, I know. That didn't catch on, by the way, in case anyone doesn't know. If anyone studied physics, we don't use that. But in all of his notes, he kept referring back to the Stoney unit, and he tried to get it to catch on, and it didn't really work in the end. So yes, that is the unfortunate aspect to it. He did try to perform an electrolysis experiment to try and measure the charge of the electron, but to this day, he got pretty close. It was pretty far, but it was kind of the closest we had to that point for sure. And what should I say about it? It was actually Millikan oil's drop experiment, and I'll talk about Millikan oil drop experiment when I cover the electric field. But the idea was there was an oil, it was dropped. There's two electric plates this way, and the oil was floating in between those two plates, and you could measure the charge of the electron. You couldn't measure the charge of just one electron though. That's a bit weird. You couldn't do that. But what you could do is you could put different sizes of drops, and there will always be a multiple of a certain number, and it was always by a multitude of 1.6 by 10 to the minus 19 joules. There is a lunar crater named after Stoney. It was there is a lunar crater. 6 years later, after all the electrolysis experiment was performed by Stoney and how he coined the term electron, we go on and about, and we get J.J. Thomson, who discovered the electron just 6 years later. So even though J.J. Thomson is given credit for discovering the electron and for the plum pudding model, maybe this is something you guys are aware of, in the end, Stoney did contribute to it, but he's not credited for much more than just that. All right, and that is everything we need to know on Stoney. We're going to do a little bit about his physics, of course. Good tea. Yeah, let's do some maths. Are we ready? Who's ready to do more maths? Sorry. Let me pick you up, chat. I'm never ready to do maths, but let's do it. Up. So that's okay. That looks good. Yay, science! Ready to attempt. So it's not just going to be maths. We're just going to cover a lot of theory as well. Where's my... You know the... that I sprayed... Yes, there you go. If you're being a bad lab rat... Good morning, Kevin. Good morning, everyone. Welcome in, welcome in. I hope you guys are having a fabulous St. Paddy's Day. In Irish lore... I think it was a symbolism, of course, but in Irish lore, St. Patrick... Oh, that's a lot of dust. I should clean that. Jesus, I get distracted easily. In Irish lore, St. Patrick chased off all the snakes out of Ireland. Which is why lore-wise, we don't have snakes in Ireland. Oh. Beautiful stuff. Beautiful stuff. No. But ignore how he ended up in Ireland. Yes, let's not talk about that, shall we, Zir? How poor Crather St. Patrick ended up in Ireland. We wouldn't want to mention that. Now I'm curious. Well, feel free to search it up. Okay, so what's his name? Oh, should I turn this on as well? What's his name? Not St. Patrick, Stoney. George Stoney coined the term electron for the negative charge of a particle. Okay? And so when we look at the structure of the atom, one of the things that we tend to show is the planetary model. But before we had the planetary model, we had these solid billiards of atoms. We just thought that atoms, kind of like the gas molecules, were just balls. Just balls floating around, whoosh, going left, right and left. But then, a very famous scientist based on Stoney's work, J.J. Thomson, came along and he came up with what we like to call the plum pudding model. This was weird to me when it was called that because I was like, what the hell is a plum pudding? I don't know. Do you know what a plum pudding model is or a plum pudding is? Because I don't. Or I didn't, to be fair, when I was younger. So, you get... I think you're meant to eat it, Program Max. Yeah, I think it's edible. I'm not sure. I think it's a UK thing. I could be wrong. Is it a English thing? It's something you eat at Christmas. Okay, I don't think we have that in Ireland. It's in Australia as well. Okay. Okay. I haven't seen it in Ireland anyway. Christmas pudding. We have Christmas cake. For sure. Anyways. So, imagine a ball. Imagine Play-Doh. I'll bring the board a bit closer. Imagine a bit of Play-Doh. Okay? And in that Play-Doh, we're going to shove in things. What we're going to shove in is... I'm going to color code this. I think this is the general color people prefer. It has positive particles embedded in it. Which we now know as protons. Oh, let me move chat away. Sorry. Chat, I'm going to take you down. Take him down, Legolas. Just so that you can see the board. Hi, guys. Welcome in. So you have this Play-Doh, and you embed a whole bunch of positively charged protons in there, and you shove in a whole bunch of negatively charged electrons in there. And this is what is referred to as the plum pudding model that was proposed by J.J. Thomson. Hi, Ultra. Welcome in. Hope you're keeping well. Yes, so we finished everything on Robert Boyle. Now we're moving on to George Stoney. It looks like a virus. What's wrong with my plum pudding model? Does this not look like a plum pudding that the English eat? It looks like COVID-19. Yikes. Okay. All right. I think it's a pretty good drawing. I don't know what you guys are mean. I'm going to continue. Then came along another person. It wasn't J.J. Thomson who came up with the next part. There was another person. And there were... I'm going to correct myself. I wanted to say Rutherford. Rutherford did a specific experiment. 2 seconds. The gold foil experiment. It's Rutherford, right? It is. Okay, he did both. Okay, Jesus, Rutherford did everything. Sorry. I just want to double check because Rutherford did more than just the gold foil experiment. Then came another gentleman, Rutherford. Now, I have a few people chimed in that they're from Australia. Is there any New Zealanders in the chat by any chance? Don't need to dox yourself too much, but is there anyone here from New Zealand? This is probably the most famous New Zealander known. As far as I know, he's on your money. What bill is he on the username checks out. He's on one of your paper monies. There's a drawing of Rutherford on it. And so Rutherford did a huge thing. He did something called the gold foil experiment. So I'm trying to draw it in this dimension. So what he did was he grabbed a very, very, very thin piece of gold foil. So you can imagine that it's just 1 or 2 atom thick. Okay, so this is kind of at an angle, but let's look at it from a slice perspective. So as if I grabbed a sheet of paper. So let's say this is my sheet of paper, okay? And then I turn the sheet of paper this way towards you, chat. So we're going to look at it that way. So it's a couple of atoms thick, okay? So thin, it's only a couple of atoms thick. It's still very, very, very thick, but to be fair. And so what he did was he bombarded this really, really, really thin piece of paper with something called alpha particles. An alpha particle is something that is a proton, 2 positively charged protons, and I'll do a different marker, and 2 neutrons. A neutron is something inside the atom at the time that was neutral. It was the moldy part, not the moldy, the gloopy part of the plum pudding model. I don't know what a plum pudding is. I'm so sorry. Do you know the thing that holds everything together? The dough. The dough. There we go. Is it dough? I'm just going to go with the dough. The dough part in the plum pudding model or in the alpha particle is the neutrons. We'll get to that in a minute. The neutron was not discovered yet. But they knew that the alpha particle had 2 positive charges of electrons. And so what they did was they bombarded. And what did he detect? He had a little detector here, and they caught all the alpha particles detected here. What did this mean? This meant that, and he calculated the percentage very, very carefully. He calculated that meant that atoms are mostly made out of free space. 99% free space. They're just empty. There's nothing in them. That was crazy. That was like, what? What do you mean? Now, a few years later, or not even a few years later, I'm not sure about the timeline, but basically, after a little while, him and Rutherford and Geiger, as in where the Geiger counter comes from, comes along and they're like just walking through the hallway. These famous scientists all knew each other. And they were like chilling and hanging out. And his PhD student comes in and he says, this is the data, this is the detection. And Rutherford is looking through the results with Geiger. And he kind of looks at it and Geiger and himself are chatting with each other. And then he goes, hold on, can you do something weird for me? Can you put the detector behind the alpha particle projector? Like, okay, I'll do that. That's a bit weird, but you know, 'tis what it is. So that's exactly what he did. The student went and put the detector behind. And nothing really happened for a while. There wasn't a whole lot. But ever so often, very rarely, but ever so often, the detector would go off. It detected an alpha particle. Again. Ding. Again. Nowhere near as this guy, because this guy was going crazy. Ding, 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 when the detector was placed behind. In front of the guy. But when it is placed behind it, ever so slightly and ever so often, the detector would go off. In fact, when you put the detector at different angles, different rates of detection were found. So if you put it over here, for example, or over here, it was detected, I think I'd like to estimate that it was roughly a little bit more here, a little bit more here than here. What did this mean? This is class. This is where physics is so cool, because this is where the genius of the interpretation of the results is amazing. What this meant was that the positively charged particles, the alpha particles, mostly went through the atoms. Because they were so big and there was so much empty space, most of them went through. However, very occasionally, one of these alpha particles got so close to the center of the atom that it was repulsed completely in the opposite direction. How would it do that? We're going to cover this in a minute, but have you heard of the figure of speech of opposites attract? So that means when a negatively charged particle and a positively charged particle are really close, they attract and pull each other. But if you have a positive charged particle and a positively charged particle, and you put them close together, they're going to repel. That's exactly what happened. As this positively charged particle was moving, it hits the center of the atom, it bounces off. So it gets deflected in this direction. It could even get deflected in this direction, or very rarely, it deflected exactly backwards. So by placing the detector all around the gold foil at different angles, Rutherford was able to show just how much of the atom was free space, and number two, just how much of it was positively charged, or how much that space took up. It was incredible, that interpretation. It was incredible work. And Rutherford absolutely deserved the Nobel Prize, jokingly in chemistry, and he has a famous quote of everything in science is physics, and science is physics, I think he said, and everything else is just stamp collecting. And I kind of see what he means by it, and it's not too dissimilar of what I say, that every field of science is just a model of physics, but he was a bit more mean about it. But anyways, he has that famous joke, and then Nobel Prize winner in chemistry. He did really class work. He discovered that alpha particles were helium particles. That was a really, really cool thing. He had amazing skill with the glass blower, where he made really, really sensitive radioactive, or made a very sensitive machinery to be able to apply a huge voltage to determine that alpha particles were helium nucleus. He also borrowed some plutonium that Marie Curie lovely and kindly donated to him, because she was able to extract it. It was really, really novel at the time. And he was able to measure that one of the forms of radiation that was emitted from uranium, plutonium, and so on and so forth was alpha particles as well. He was a fascinating individual. Rutherford is one of my top scientists when it comes to what he contributed and how he interpreted the results. It was amazing. Welcome in, Fido. Hopefully your stream went well. Welcome in, welcome in. How you guys getting on today? What did you do? What if the alpha particles collide with it completely bounces back. So let me show you why. We're going to move on to now the planetary model of the atom. So the planetary model of the atom said that the nucleus, the guy in the middle, is positively charged, and then the electrons orbit like planets around it. This is the planetary model. So what was happening was, when these positive alpha particles were coming in, most of them were just going through. They were just going whee! Because it was free space, they went whoosh past it. But very rarely, this alpha particle was approaching the proton, the nucleus of the atom. Positive and positive repel each other, and it just bounced right back. Or if it got too close, it could have been, deflected a little bit. or deflected this way. And he interpreted those results. He did proper calculations on this to actually determine the size of it to such amazing degree of accuracy. This is incredible. This was in the early 1900s. I think this was like way, way, way before the turn of the century. It might have been like 1898 or 1899 when he was doing an experiment. To put it in perspective, there was a whole bunch of scientists and physicists during that time who were like, yeah, the atom isn't even real though. There was so much pushback to this interpretation of the results. There was like, not only did they not like accept protons and electrons and God knows what else, they didn't even accept the atom half the time. A few people got really stressed about this. Infamously, Stefan Boltzmann did a lot of stuff on statistical physics and atomic theory. And obviously he was also suffering from a lot of stuff personally, but he was shunned so much by his community that he did end up committing self-murder. And yeah, it was this is really crazy. So I say this all the time. And so when we want to change something really, really big in physics, you kind of need to weed out the old generation. And that's kind of true about most things, politics, social norms. Young people come in, they learn on what previous people did, hopefully. And over time, it takes a long time to make change possible. And the same thing happened in physics. When Einstein and Planck came out with, Planck's constant, light as a photon and all of that, they had a huge amount of opposition from physicists. It took many, 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 many years before that was accepted among the scientific community. Quantum theory absolutely revolutionized everything, but it took a lot of push, a lot of effort, and a lot of scientists to make this happen. Yeah, something to kind of... Anyways, I ended up ranting about this a bit too passionately, sorry. How's everyone's rendering of reality going? That's lovely. That's a lovely figure of speech, actually. Hello, welcome in, everyone. The academic community can be brutal, you're absolutely right. I recently, just last week, got my reviewer comments, from Reviewer 2. Absolutely got destroyed. Brutal. It's brutal. Academia is tough. It's not for the faint-hearted, for sure. How can these positive particles be bundled and shot at the atom? Well, there's certain atoms that emit them naturally. So uranium, plutonium, all those radioactive materials that were being researched a lot. Marie Curie, Pierre, Becquerel, Geiger, all of these guys were doing loads of research in radioactivity at the time, and they knew that particles, well, Rutherford actually discovered before that they were emitting positively charged particles from this. And they were going, is it called transmutation is the word? We are going to cover that when we talk about Walton. It does. It has. This was extraordinary evidence. The beautiful thing about physics and just the scientific method, and this is why I think even a lot of people might say that history isn't science or this isn't science. Almost every field, not just science, just field of subject, has some sort of element of a scientific method. It's something established by the community of, look, if your thing works, it needs to undergo some rigor. So it needs to do A, it needs to do B, it needs to do C. Now, physics has been around since the ancient Greeks, even longer before that, and other civilizations all over the world. And so a lot of different civilizations contributed to the scientific method, and it developed over time. One of the people, we have quite a Eurocentric view of science. I do. I was grew up in Europe, and I studied all of that. But if you look through the history, one of the greatest contributors to the scientific method was Ibn al-Haytham during the Islamic Enlightenment age. There's so many people around the world that contributed to science outside of Europe, and just because we were such isolated nations, we didn't get to know them, or they developed them separately. Once we put it all together, we can get a very conclusive scientific method and rigor where you put it to the test. You have an idea, you put it to the test, and you do everything you can to disprove it as well. And once it holds up to all arguments, you have a solid theory. But it doesn't mean it's right. There's models. There's just models. So remember, we had the plum pudding model. That works. for certain amount of physics, that works. Then we have the planetary model, that works. But for many, many people, that wasn't good enough. And that's where quantum mechanics comes in. We're not going to touch that because I don't want to touch that. Oh, I feel the same, Time Tales. I want to learn so much, but I have so little time. And not too many years later, actually a good bit later, about 20 years later, the neutron was discovered. So it turns out that when they started weighing the atoms, they were heavier than just a proton or two in there. So it turns out atoms have a neutral particle in there, bounding together with a strong nuclear force. There was neutrons in there from the word neutral. Okay, now that we've covered the atomic structure, let's talk about some dudes revolving around the electron. Let me get my spray bottle. Go. Oh my god, my demon... Oh, Jesus Christ. That's not what you want to happen to your demon core. I'm just saying. I'm just saying. I might sit down and fix it later. So that's how it happened. Historically accurate depiction of what occurred. Quick, get the screwdriver! Yeah, I'll fix the demon core later on stream. I want to show it to you. It does glow. It's really, really cool. I also have a video, actually. Yuli, Tariq, Medjay, I know you guys are very, very busy already modding, and I really, really appreciate it. You could... One of you could fish it out, the YouTube video. I'd be grateful. The demon core one. Just to see it glow. Okay. I'm getting a bit hungry because I didn't have breakfast, so I might have a yogurt in my next break. But yeah, so it won't be clean unless I spray a bottle, so it needs to dry a little bit. Whoosh, whoosh, let's dry it. Okay. I have my laptop here in case anyone's wondering. I have a little bit of notes, just a guide on what topics I should cover first. So usually when I teach this, I go through the history of Coulomb, of static charge. I bring a Van de Graaff generator in for my students and I shock them. Essentially. And yeah, I teach static electricity first. But that's not the point of the story. Thank you, Zier. Really, really appreciate it. Zier, I forgot to mention that you're here. Zier and Hax are here as well. Apologies. Thank you, Zier. El Joel, thank you so much for your prime. Really, really appreciate it. Thank you. I'm so sorry, Zier. You were here very, very active as well. Apologies. Very rude of me. Thank you so much for your prime. Really appreciate the support on this channel. Okay. Ooh, this is my first time tuning into a science and technology stream. The first thing I see is, oops, I knocked over the demon core. That's a good stream. You know it's a good stream. So the first equation that we're going to cover is a gentleman by the name of Coulomb. And we're going to cover something called Coulomb's law. And if anyone studied Newton's gravity, you're going to be like, he copied his homework. Turns out this is a very relatively popular equation in physics. Ah, thank you, Jay. Really appreciate it. Hey, Wolf, welcome in, welcome in. Assassin's Creed, I swear I thought you were playing Cyberpunk yesterday. I'm imagining things. Thank you, Tara, for giving a shout out. Thank you, Zier, for linking the Demon Core. And thank you for clipping the Demon Core incident, Jay. Yeah, I got these markers. They're really nice. They're super thick markers. Look at the size of this guy. Massive. Chunky boy. Yeah, I need them because when I post stuff on my social media, if you guys want to check on my Instagram and so on, I post a lot of derivations and maths on social. The lighting can be quite bad, so I need to make sure that it works out very well. Hello, a physics class. Welcome in, welcome in. Okay, so what is everything in this equation? Let's look at this. This is force. Does anyone remember what your unit for force is? Or your hand is just tiny. Fair enough. What's the unit for force? Newtons, exactly. And you might be saying, but tofu, that's mechanics. How could you be using this in electrostatics? Interesting, isn't it? It turns out all these parameters are across the field true. Q is a symbol that we use for charge. So this is, in coulombs, the charge of particle 1. Hence, charge particle 1. Meant to be 2 here. So take a wild guess. Q2 is charge of particle 2. Let me just close the blinds here. I think you don't see the board. There we go. I think the lighting is a bit better. And the next part is we have R. Now, you might say, well, we use displacement or distance, S or the letter D. Why are you using R? Well, they're all valid. S, D, R, and X are all notations that we use for expression of distance, and their units as meters. But there's ever so slightly different interpretations. For example, D stands for distance from A to B. S would be displacement, so it's a distance with a given direction. X is usually position, so X could be 0, your coordinates, and then your other position, X2, could be 2, 6. So it's usually referred to as position. And finally, R usually refers to radius. We tend to kind of talk about circular motion in a lot of these things. That's why I use the symbol R. But don't be too startled. It's just the exact same thing as distance, okay? So, what that means is, last part, K. Hopefully you guys are catching on. Coulomb's constant. It's just a constant. So if I grab two particles, a positively charged proton and a negatively charged electron, it means that there is a force of attraction between these two molecules. The proton wants to go in this direction and the electron wants to go in this direction, and they have a value of a force. And how to calculate it is, well, Coulomb's constant is just a number. To know the charge of the proton, 1.6 by 10 to the minus 19 coulomb, the charge of the electron, 1.6 by 10 to the minus 19 coulomb, and the distance between them. So as long as you know what the distance between these guys are, you can calculate what the force of attraction between two charged particles is. And if I change this to a proton, the arrows would be in the opposite direction. They'll be repulsing, but the value of the force would be the same. I like how I'm supposed to be studying, but I'm watching this instead. Fair enough. That means the closer the particles are to each other, the more the force of attraction is. Kind of like the law of gravity. It's exactly the same if you guys remember Newton's gravitation law. G times m1 times m2 over r squared. The further apart they are from each other, the less the force of attraction is between them. Jesus, Puffy Nick, you've been following since the Heroes of the Storm days. Welcome in. Not magnets, charges. Magnets behave kind of similarly, but they are different. But charges, we're talking about charges. Okay, do you know what? It's one thing to show the equation and say, lol, this is what it is. How about we actually calculate what is the force of attraction between a proton and an electron that are 10 centimeters distance from one another? Well, if you measure the force and then you know what the charges are and you know what the distance is, you repeat the experiment over and over and over again, you will always get the same value of a constant. So that's how it was determined. I don't know the exact experiment for that particular thing, but that's usually it. I think it was actually Coulomb now that I think about it. No, it wasn't Coulomb. Anyways, let's do the maths. Someone tell me Newton, Coulomb's constant. 9 by 10 to the power of... Nine? I'm going to have to ask someone to check that. It's 8.99 by 10 to the power of 9. Is that correct for Coulomb's constant? What in the name of education is going on? And then the distance isn't 10 centimeters, it's 0.1 meters b squared. Google says it's 8.99 by 10 to the power of 9. Perfect, thank you very much. I rounded it up to 9 because I am what we like to call an efficiently lazy physicist. All right. If anyone still has their scientific calculator from school, make sure to grab it. 9 by 10 to the power of 9 multiplied by 1.6 by 10 to the power of minus 19. Oops. The power of minus 19 to be squared. Again, I'm being efficiently lazy. Divided by 0.1 to be squared. We get an answer of 2.304 by 10 to the minus 24. Did I do that right? I think I did. I only know that 2 plus 2 is 4. What about PEMDAS? I don't think we did anything wrong there. So that is the force of attraction between a proton and an electron that are 10 centimeters away from each other. It's very, very small. It is. It's very, very tiny. So when we do with electrostatics, even though there's an infinite distance between particles and we can calculate it, we only really work with them either with really large charges or with very small distances, or a combination of both. Ah, Jesus. See a fellow Irish with the use of language. I got 2.3 by 10 to the minus 26. Oh. Let me double check my maths. So, 1.6 by 10 to the minus 19. All multiplied by 1.6 by 10 to the minus 19. All multiplied by 9 by 10 to the power of 9. All divided by 0.1 b squared. 2.3. Oh, yeah, you're right. It's 20. Oh! Okay, I just misread my calculator. It was 24. I need to get new glasses. I can't see. It's even smaller. The force of attraction between those two guys are smaller. Now, the way Coulomb discovered this was really, really cool. So what he was doing was, he was a Frenchman, and he was in the military. He's very, very smart, and he decides after his military service to work on science, work on discovery, work on all these kind of different things. And what he does is he tries to develop a very, very sensitive and very good compass. So what is a compass? It's a circular disc, and there's a little needle in there, and it moves freely, right? So that it can point to the magnetic North Pole. It's actually the South Pole, by the way. And it points north. Now, what he wanted to do, wanted to study friction. He wanted to remove the friction of the needle so that it could move even more freely. And he did it in such a beautiful designed way that when he walked into a room with his compass set up, the needle moved. When he walked around, the needle kept pointing at him slowly. It kept pointing at him. He was like, what the heck? What was actually happening was he made his little compass design so sensitive that it was quite literally measuring or pointing towards charge. If it was ever so slightly negative charge, it was pointing to anything so slightly positively charged. And so he did a whole bunch of experiments on it and developed this equation for Coulomb's law. Before the electron was even known. I don't know. To me, these things are so cool. They didn't even know about the atom and they developed these kind of things. So that is where Coulomb's law came from. It was in the process of making something that they end up discovering really amazing foundational research or, foundational physics knowledge in this case. Was he a bad person since it pointed at him? I don't think that that's what it's got to do, but no. That is Coulomb's law. I think that's everything we know about it. I just have my lecture notes. If anyone's wondering where I am. Yeah, I think we'll just talk about the electric field now. The electric field is definitely the next thing that we want to do. Anya and Vert, welcome in, welcome in. Hope you guys are keeping well. Yes, the circumference of the Earth was calculated thanks to Eratosthenes. He measured the shadows during the sun equinox? No, what's it called? 21st of June? Whichever one it was. Yeah. And yeah, you can actually, so is the solstice, I forget what it's called again. Yeah, with sticks, exactly. Yeah, we did the maths on a stream once before. It was really, really good. Hi, Lunatic, welcome in, welcome in. Love to see you here. Super interesting. Ah, thank you. You're very kind. Hi, Sid. Welcome in. Welcome in, everyone. Okay, so now that we've covered Coulomb, he was a pretty cool dude, Coulomb, and discovered all of this, we're going to talk about the electric field. So what is this? The electric field is kind of something that you might know from sci-fi. You know the way there's those movies and TV shows, and they have these like shields covering them and protecting them from laser beams, and there's the field in Star Trek, you know, the shield that's across Star Shield. Said that poorly. The shield over the starship. All of these kind of things are, how should I say, embedded with some terminologies in physics. And one of the classical ones that they tend to talk about all the time is the electric field. And it's actually not too dissimilar to Newton's law. Let's keep actually Newton's, well, not Newton's law, Coulomb's law. Let's keep that up there for a second. We're just going to clean this up a little bit. Ugh. Oh, okay. So what an electric field is field. And you might be familiar with the field because gravity is a gravitational field, really. We oversimplify with Newton's laws and so on and so forth, but reality, all of these guys are just fields. What we mean by that is, remember there was a negative charge electron over here, and then we have a positive charge electron here. Ignore the negative electron, generally speaking. What we mean by a field is, if I were to throw, okay, we'll even ignore it. Okay, we'll just say that over here, there is something that is super, super attractive to the proton. When we draw an electric field line, what we mean is if we throw a test charge, basically a massless little thing, if we were to throw in a positively test charge in the field, where would it go and how quickly? That's what an electric field is. It's this entity that we do not see, but fields exist all around charged particles and also between potentials. We'll cover that in a second, by the way. There's a lot of things happening. So let's say I took a positively charged proton. Sorry, it's still not dry fully. So let's take a positively charged proton. And it induces a positive field around it, okay? It induces a field, an electric field around it. And because an electric field line expresses it, that this is where it would move if a positive charge was placed it. What I mean by, okay, what does that mean? If I were to place a positive proton over here, massless, not real, in which way will it go away from this guy? Well, we'll go this way. Cool. What if I were to place another positive charge proton over here? Which way will it go? This way. And if I placed another little guy over here, this way. So as you can see, the electric field made by this proton is completely outwards in its direction. What if it's an electron and I put a little positive charge over here, what we call a test charge? Where would it go? It'll go straight into the electron. And so this is how electric field lines are expressed diagrammatically. I hope I said that correctly. Okay, sure. Chat is like, that's easy. Arrows pointing in and arrows pointing out. Okay. Let's make things interesting. They're two different phenomena. They're interchanged between each other, Fuzz, but we're not going to talk magnets. Magnets are perpendicular in the other direction. We're not going to talk about magnets. We're going to talk about just electric fields. They can operate similarly, but they are different. Okay. Positive moves towards negative, exactly. Oppositely charged particles move together. Same charged particles move away from each other. Draw me the electric field lines around two of these particles together. Do you just genuinely go to work, teach, get home and teach more? Kind of, except I never teach in the evenings after work, so I only teach on my days off. Yeah, but I'm a big fan of education all across the board. Some call me a psychopath. Anyways, in this case, remember it's repulsive, right? So the electric field lines are going this way, this way, this way, do, and the guy's same here. There's electric field lines created from here, do. But what happens when these two electric fields meet? Ew. This guy's coming in, ew. This guy's coming in, ew. Because remember, they're repulsive. And so they all kind of curve outwards away from the positive charge, and just like that around the rest. This is what the electric field looks like between two positively charged. They push away from each other. They don't mess with each other, exactly. So two positively charged particles push away on each other. What about these two guys? They're attracted to each other. They're best buds. They wanna be together. How does their electric field line go? Well, remember, it's what the positive. Where would the positive guy go? Do. And this is what a combination electric field line like. So an electric field are arrows. The more arrows I draw, the stronger the field is. And if I were to throw in a positive charge in here, into those lines, we're asking it, well, where does it go? That's what an electric field is. If you put in a little test charge, you just throw it in somewhere in those field lines. Where does it go? In which direction? And by how much? That's what an electric field is. So your electric field might not be constant. You can imagine that the electric field is different to here, which is different to here, which is different to here. So distance is an important thing. And it depends where. Is it here, or is it here, or is it here? So depending where you throw in a positive charge and where it goes, it might be a bit confusing and weird to know or determine where it goes. So that is what an electric field is. After I've shown you this, can I ask chat, do you think that an electric field is a vector or a scalar looking at this? Yeah, no, it's simultaneous, Dark. You're absolutely right. So one is pushing while the other one is pulling. It's a vector, exactly. Because we gave it a direction, it is a vector. It's pointing towards something. It's going towards something. So, you can imagine that it also depends by how much it is pulled. So if we wanted to mathematically express what an electric field is, we could show that.
Looks like meat's
Back on the menu, boys! Thank you so much for the videos, appreciate it. Ah, thank you, puppy, I appreciate that. You're no problem at all. Does medium matter for electric field? Yes. It's called a dielectric material. The ability for material to induce a electric field. Wild party last night. Ah, I see. Well, just don't get sick. Come in, sit down, and behave in class. Or the vigilators. What is it called in your universities or your schools? The guys who go around and make sure you don't cheat in the exam. Vigilators? Yeah, the mods are the vigilators in this class today. We can express the electric field as a vector. It has direction because we know in which direction it's going to go. As the force per unit charge. We want to know how much that charge is moved by the implied force upon it. Okay? We're going to have some fun here. Oh, before we do that, what's the unit for an electric field? F is Newton. And Q is a charge, so it's Coulomb. So the SI unit for an electric field is Newton per Coulomb. It's not the only one, by the way. So here we go. We know something about the force, don't we? We just said Coulomb's law says that KQ1 and the test, we'll say test charge over another charge, it doesn't matter, over R squared is equal to F. Let's sub that guy back in. That's KQ, capital Q just to differentiate between the Q's, over Q here, R squared. Let's look at that equation. Oh, would you look at that? Would you look at that? Very interesting. We can cancel those guys off and we get a very interesting equation. KQ over R squared. We have a new expression for the electric field. We can calculate, if we have a charge, if I put a positive field here, a positive charge here, and then I say, do you see this point over here? What's the electric field over there? Or what about the electric field over there? And you know what? Can you tell me what's the electric field over here? What you need to do is you need to know obviously what the value of the charge is, Q, and the other guy you need is the distance. So as long as you know what distance away you are from the charge, you can calculate the charge, the electric field induced there. Now what's interesting is, when we have two particles, you just treat them as two separate electric fields. So you'd calculate what the electric field is, let's say here, due to this guy. Then you'd calculate the electric field from this guy's perspective all the way over there. And you add or subtract them together. By adding those electric fields together, you can get what the total electric field is. And so you can put in more charges and calculate all the electric fields, get the sum of them, and you'll know exactly what the electric field is due to all the particles. Just an algebraic sum of them. And there we go. We have an expression for the electric field. Where do we see electric fields? We're going to go towards particle physics in a little while. But electric fields is how we get particles to move super fast. Well, think about it. Maybe I know. Again, I don't mean to dox our ages, but I know that many of us, not all of us, but many of us, are perhaps from an older generation. Do you guys remember your cathode ray tubes in your TVs? Does anyone remember putting their hand on the staticky TV and the static that you get from it? Okay, yeah. She's calling us all. Yeah, there you go. What it was a beam of electrons being emitted, and they had electric field plates to bend the electrons from one way to the other before they bombarded to the TV. So you could, this is your screen. This is where the electrons were being emitted. There's a whole bunch of other stuff, but there's electric fields or magnetic fields. That's another thing we'll talk about. And as the electrons were going through here, they deposited on the screen, and that's where you got your image. You can imagine that they bombarded a bunch of electrons over time. That's where you get the statics feeling when you put your hand on it. That was quite literally electrostatics being built up on the TV because of, well, the electrons bombarding it. That's where you see the electric fields. Another more common thing is accelerators, which we'll get to today. That's one of the big topics we're going to cover, is when you apply a voltage, that's the next part I will be teaching, do not worry. When you apply a high voltage, you induce an electric field. Electron will go to the... Then the electric field is in this direction. I had to think about it. This stuff is hard. You can't learn this stuff off. Well, maybe you can. But you have to think about it. So an electric field is induced. So when you throw in an electron, you can speed up particles. The higher the electric field, the faster it's going to go. And someone mentioned something earlier. F is equal to A. Beautiful stuff. We have F. This is Newton's second law. We have F because it's usually in Coulomb's law or somewhere placed and embedded here. We have mass. We have acceleration, which means what's really cool is if we know the mass of the electron, which by the way we do know quite accurately, we can calculate how quickly the electron is accelerating. If we know the distance between the two plates, we can actually calculate the speed of the electron as it bombards into our TV. So you can actually do some really cool maths with this, even with first year level physics. Yeah, in case you're interested or opening up to a bit of curiosity there. We are not finished this topic. I'm just running out of oxygen to breathe. So what I'm going to do is just take a small quick break. I haven't had breakfast yet. It's 11:30. So I'm going to have a quick yogurt, a quick pee, make a cup of tea. So it'll probably be a 5-minute break. I will still keep you on the topic of physics. By running some ads. There's a little I have a whole bunch of YouTube videos sprung together of different physics topics that I teach. Stream is also running out of frames, is it? Did I drop in frames? Oh, I did drop frames. Whoops. No, that was me. I dropped frames. It looks like I'm not dropping anymore though. Am I still here? I think it's fine. It looks like I haven't dropped a frame since. I figured that was me. No, that was me. Something happened there. All right, I'll take a quick break and I shall see you all lab rats in a few moments. I would like those 5 seconds of my life back. I think like companies can pay to be on the front page. I'm not sure. But the reason I got the front page is because partners have the ability to apply once a month to the front page if they propose something interesting. So for St. Patrick's Day, I proposed to teach stuff about Irish physicists or physics around Irish physicists. And yeah, they accepted my application. And that's why I am on the front page today. The money to be on the front page comes out of mods' wages. Oh my goodness. Oh my goodness. Hi hype train. Level 5. Oh my goodness. Holy smokes. Thank you so much for a level hype train. That's incredible. Thank you so much for the support. Many primes, many PP points as well. We appreciate the PP points, the Partner Plus. Means a lot to us. Means we get a bigger share of all those subs that were gifted. My spoon just fell. Oh well. Okay. Put my laptop.
And they call it a mine.
A mine! KS time. Thank you so much for your sub. Really, really appreciate it. Partner Plus Points needs an acronym. It's PP! That's the greatest acronym for it.
Looks like meat's
Back on the menu. Oh, lads. Jesus Christ. Thank you so much for all the subs. Really appreciate it. Silver, thank you so much for the 100 bits. Lara, you're very, very kind. And
They
for
call
6
it
months.
a mine. A
You're
mine.
crazy. That means you've signed a lab rat contract that I can use you for experiments for 6 months. Willingly. You willingly signed it. So before you subscribe to this channel, there are terms and conditions. If you support this channel with bits, subs, or any way to ensure that this channel keeps running, I would like to highlight that you sign a contract that you're going to be part of Tofa's laboratory as one of her lab rats. This means that she can use you in any way that she sees fit for experiments, science, and for the prosperity of lab rat kind. Thank you so much. Thank you, Time. You're very, very kind. So, now we talked about Coulomb's law, number 1. Number 2, we talked about the electric field, and the last guy we need to talk about is the electric potential. And kind of in the name, it's the potential to do work, or the potential to get things done. Every single one of you lab rats has the potential for greatness. If only I did not stand in your way on the front page of Twitch teaching you God knows what at this stage. I watched the 3-body problem. I didn't enjoy it only because people forced me to watch it, kind of, and said that it has amazing physics in it, and I was a bit... But honestly, if I had not been so bullied into watching it, I think I would have enjoyed it better. There we go, Hex. We're very similar. Without coffee, I have no potential either. Thank you so much for the bit. Here is one bit to sign me up as an official lab rat. So, electric potential. We're going to do a tad bit of derivations. Has anyone ever told you you look like Grace in Peak? No, not Grace, no. I've heard Uma Thurman. I've heard... Yeah, no, it's just really Uma Thurman. That's the only one I've heard of. The closest celebrity lookalike I've been told. If anyone finds anyone closer. We're going to do a bit of derivation here. You look like Richard Feynman. Thank you. I'm going to take that to my grave. Appreciate that. Appreciate that. So, if you guys remember, potential energy is equal to minus work. You're pushing, it's in the negative direction. Potential energy and work are the same thing. They're both joules, right? They're both energy. They're a form of energy. Potential energy is the energy that you have the potential to do, and work is the actual work that you do, but it has the minus sign because it both can't be true at the same time, right? So potential energy is equal to minus work. They're both two forms of energy. Their unit is joules. Now, if you remember from physics, mechanics, work is equal to force times distance. So if I wanted to measure how much work it takes to push a block across a table, I would measure the force that I'm applying multiplied by the distance. The force is equal to mass times acceleration. We can, calculate all these kind of different things. So work is equal to force times distance. Cool. Remember I said that the electric field is equal to force over charge? Remember that? Well, let's rearrange that equation. Q, E is equal to F. We could sub that back in for the force equation over here from classical mechanics. So this F go right over here. Tons of potential, no motivation. Sure, that's the story of life. Doors Maniac, that's the story of life. Work is U, E, D. I always forget what it stands for in Latin properly, but my maths teacher always said that it stands for quite easily done. Hype train complete, level 6. Thank you again so much for the bits and for the subs. I really appreciate the support on this channel. It does mean a lot. We have a few things, you know, to buy for this community. We have a fume extractor. The next thing, I wanted to buy some stuff. I wanted to buy a microscopic camera. That's one. A few things. My big thing is the oscilloscope and the frequency. We'll wait for those. Steph from the Goonies is still a celebrity. I haven't seen the Goonies in a long time. I don't remember who that is exactly. So work is equal to the charge of a particle, the electric field, and the distance. By pure mathematical derivation, we can confirm this. So, what are we going to look into? When talking about charged particle in an electric field between two plates, so remember we talked about two plates earlier. 0 volts, 100 volts. I know we haven't covered it yet. Don't worry about it. Oh, thank you, Fates. Quaderes demonstradum. Stradum. Dum. One or the other. Got close enough. And there's an electric field. Okay. I saw that microscope. It was really, really cool. Yes. Where was I? So work is equal to QED. The line's correct. And so to get from a potential, from a point of high potential to a potential, to a point of low potential, from potential E high to potential E low, the work has to be in the opposite direction. So the potential energy, or the change in potential energy, is equal to minus QE. We're going back to the first equation. Okay, so we jump all the way down. We say work is equal to QED. Sub it back in here. PE, potential energy, is equal to QED, minus sign in front of it. Are you a professor? No, I'm a lecturer. In Ireland, we don't get professorship for being lecturers. In some universities around the world, as soon as you're a lecturer in a university, you're a professor. Here, it's a rank. You have to apply for it. And the only way to apply for it is you have to wait until a position opens up. So basically, you have to wait until another professor dies before you apply for it. So I'm just waiting around for now. So no, I'm just a lecturer and a researcher. Oh, thanks, Cake. Welcome in, Cake. So that's the system we have in Ireland. We're trying, I think there's a push for some Americanization at the moment. There might be other ways of getting professorship now. I've heard a few things. But as far as I know, at the moment, my title is not lecturer. Just a lecturer. Just a researcher. Okay. But I have a permanent position. Like this is my permanent job. All good. Yeah, so the way it used to work anyway, I don't know if it's changing. Like I said, there might be change happening right now. I'm not aware of all the details. Is that there's only a fixed number of those positions available for each university. And if you get more funding from the government, you can have more positions. Yeah. I'm not sure. Again, take what I say with a grain of salt. With a huge grain of salt. Okay, so we've derived that the potential energy is equal to the charge of the particle times the electric field times the distance. This is an important derivation. Doesn't mean much to us, but I'm going to let you sit on that for a second. We're going to solve another experiment. We're going to do another part here. No, not my real lectures in university. I teach privately. I don't know how to say it. But then, you know, I do whatever I can here. What level of physics is this? This is general physics. So this is introductory level. So you'd either see this in first year crash course physics, or you see it in like high school level when you go into physics first. Okay, maybe not junior cert level, but definitely leaving cert level. That might be an Irish term. Junior year, senior year? No, sophomore year, senior year, middle school, high school. Yeah, maybe it's middle school. Would that be the best correlation? Every education system is different. So in Ireland, we have primary school, where you're there from 6 years old all the way to 12. And then we have secondary school, kind of like high school. We start anywhere between 12 and 13, all the way to 18 before you go to university. But we divide that section into junior cert and leaving cert because we have two examination process. Junior certificate and leaving certificate. So junior certificate, you're introduced to science properly. This is maybe not covered, but then in leaving cert, so before you go to college, we would cover this, yes. Yeah, we're doing electrostatics at the moment. Yeah, high school, yeah. But again, we would teach this very, very quickly in first year physics as well, because not everyone gets an opportunity to study physics, unfortunately. Okay, so similar with the electric field, it's better to understand electric field as force per unit charge. Remember in electric field, we said that electric field is equal to the force per unit charge. Well, the potential is the exact same idea. We want to know that it is the potential energy per unit charge. So electric potential, that's where it comes. Potential energy, specifically delta potential energy. Remember, it's the change of potential. This doesn't mean too much. We'll get to there in a second. Potential energy over Q. Well, I have an equation here for potential energy. Couldn't I sub that in? I could. You're absolutely right. So we would say minus Q D over Q. A bit ugly there. Now, because it's the change in potential energy and there's a minus sign, we're not going to include the minus sign. And maybe that's going to kick in a little bit. Suddenly we don't have a directionality associated with it. Cancel the two Q's and we get have the expression for voltage, potential difference, as voltage is equal to electric field times distance. So what does that look like? What does that mean? Because so what TOEFL derived it mathematically, but what does that actually mean?
Does not simply walk into Mordor.
Hey, Smirky, thank you so much for the raid. Welcome in, Raiders. Welcome in, welcome in.
Red alert. All hands stand to battle stations. Lay in and intercept course of the Romulan ship.
Shields up. Load all torpedo bays. Stand by phasers.
Warp factor 8. Engage.
Welcome in, welcome in. Hope you guys had a wonderful stream. We're just doing some maths, some physics, and we're just defining what electric potential is. Shields up with the electric fields. Voltage is equal to the electric field
Does not
times
simply walk into
distance.
Mordor.
Very, very interesting. GMAT, welcome in. Okay, look, we have to do it back to back. Back to back. Double raid. Defend the
Red
stream.
alert. All hands stand to battle stations. Lay in and intercept course of the Romulan ship.
Shields up. Load all torpedo bays. Stand by phasers.
Warp factor 8. Engage.
Thank you so much for all the raiders. Welcome in, welcome in. Hi, Lasse. Welcome in. Happy St. Paddy's Day. You going out for... I wonder, will you be taking your little munchkin out for the parades or anything? Unfortunately, I'll check the weather again. Oh, at least it's not raining anymore. Yeah, the weather isn't great. Typical St. Patrick's Day. The weather's just a disaster. Oh, she's sick. Fair enough. Fair. I hope she's okay, and I hope you're taking care of her. So sorry to hear she's sick. It must be very stressful. Hey, so you might have noticed that I said something a bit odd. I said electric potential, but then I said voltage. Okay, chat. I need you to buckle up. Okay, buckle up. Are you ready for this? There are so many words that we use in the English language that almost mean the same thing. Now, I'm pedantic with some of them, but I'm just going to cover them. One of the words that they use is EMF, the electromotive force. I don't like that. That's outdated, and it is used incorrectly in many, many terms. Don't use it. Number 2, we might say electric potential. Number 3, we might just say the word potential. We might also add potential difference, and then we might say the word voltage, and then we might say voltage difference, and then in a circuit, we're going to say voltage drops. 7 things I mentioned there. The units for all of them are volts. We're still referring to them as voltage. All mean the same thing. Some of them are a little bit more pedantic in the definition. Skylar, thank you so much for gifting a community gift sub. You're very kind. Thank you. I hate when it's like this. Exactly. So from here on in, I will use the term potential, potential difference, voltage, voltage difference. So those are the 3 words I will ever use. Potential, voltage, and difference, or a combination of those 3. They mean the exact same thing. The reason why it was developed and changed over the years is because the understanding of electricity, and the understanding of electrostatics and this field of science developed over the years. Some people were too old school, some people were too new school, and sometimes people made very, very pedantic definitions for certain things. So I will not use the term electromotive force. That's a very specific thing. Voltage drops are a very specific thing. I'm keeping away from those terms. They mean something very specific and students use them incorrectly. So just bear in mind, I will say voltage, voltage difference, voltage potential, potential. Those are the types of terms that I'll be using. Zoned out in differences. But there is an important term to point out here. What I really want you to take from this is that word difference. That means there's no such thing as voltage at a point. Remember when we were calculating the electric field, I would put a charge here. And I said, well, chat, could you calculate to me what is that guy over there? Right? Remember we would do that. We would get the distance, we'd know what the charge is, and we could sub it in the maths and we can calculate it very, very accurately. You can't do that with potential. Potential is potential difference. So when we drew those plates earlier, notice that I had 100 volts here and 0 volts. So the potential difference is 100 volts. 100 minus 0, it's 100 volts. That's why we're so pedantic about that terminology. Just to be mindful, there's no such thing as voltage at a point, even though people say that and it pisses me off. There's no such thing. No such thing. And if your lecturer says that, you can correct them. Okay, don't call me out because they're going to come at me then. Anyways, now that I've covered that, voltage difference to the electric field times distance. And remember we calculated electron. That means that if I were to throw an electron here, or like if I wanted to understand what the potential is, if I didn't know what I was applying, if I didn't know what the voltage was here, I could calculate it by knowing what the electric field is and the distance. That's kind of not true in real life. Most of the time, we actually know what we're applying, because that's usually what these power supplies are all about. Here you go. I have a power supply right here. So a power supply, I'll turn all these nooks and crannies and knobs, right? And I'll set the voltage and I'll set it to 10 volts. It's usually something that I know. However, I have no device at home to measure the electric field. So it's usually, exactly, Skibbity. It's usually the electric field we calculate. We know the distance between the 2 plates. We'll know the potential. That is usually how we will calculate the electric. Interesting. Remember I said that the unit for the electric field Newton per. What's the unit of the electric field? When we have these 2 parameters in there. It's not got to do with directionality, Edo. It means that it's exactly the opposite. So if you have potential energy and you've work, energy conservation laws, they're constantly switching between one another. So if you've maximum potential energy, it means you're not doing any work yet, and it's 0. That's where that minus sign comes from. It must be exactly opposite. It's not joules, no. What's the unit for voltage? It's a volt. The unit for distance? Another unit for the electric field is voltmeter. I always try and recommend everyone not to study this off, not to learn off the units, because I never remember you. Obviously know your SI, distance, weight, mass, time, all those good stuff. But I never remember what the field is. I never do. I always have to do a quick little mathematical thing just to remember it. Always in the exam and the test, if you're doing this for yourself in studying, what I highly recommend you do is never learn things off and try and figure out these things off. No, amps is current, and we're not dealing with current. This is voltage, distance. Electric field is different for that. We're not talking about Ohm's law, if that makes sense. Not yet, anyway. Well, we're not going to be talking about it today. Okay. Voltage is E times D. It's also the same thing as E times R, where we've been using distance as a symbol R for the longest time. We have an equation for electric field earlier, don't we? Yeah, chat, we do. We do have an equation for it. It was KQ over R squared. R. Huh. I think we can cancel something. This R cancels R's. And we get another expression for voltage is A is equal to Q. So this is a way of measuring the voltage, the potential energy, potential difference, at a point of a charge at a certain distance. Okay, so that means that we can measure, I know this is awful and I hate the language and I just said don't do it, so bear with me. If I took a charge like this and I said, chat, could you measure the potential for me at a point here? If you know the distance between them, you know what the value of the charge is, you know this is just Coulomb's constant, you could always measure it. Now, I showed you so many equations today. This was very, very mathematical. A lot of you might be overwhelmed, and I'm going to be honest, this is as mathsy as it's going to get. You survived the trenches with me today. You'll survive everything else today. Today is good because we're going to do a bit of particle physics, which is a little bit more fun. And then we're going to do some X-ray diffraction or laser diffraction. We're going to wear safety goggles and everything on stream. And we're going to calculate or show how scientists measure the size of atoms and molecules and bonds. Thanks to all these famous Irish physicists. So I'd just like to finish by summarizing all the equations for all of them. They look so much better when you put them all together. Ah, class! Archaeology is really, really cool though. You're more than welcome here, more than welcome. So, we said Coulomb discovered Coulomb's law between two inverse square distance between them. Measure the electric field at any point, you grab the charge, and whatever the point is over the distance squared. And then we said that the electric potential is the potential point around the charge at any given point, the distance over R. It's kind of easy to see it now. Yeah, sure, we just got rid of a Q over here, and that's how we got the electric field. And over here, we just got rid of an R, and we got the guy over here. So now what you can do is you can see how these guys correlate with one another. This was the equation of E F over Q. Go. And the guy that brought these two guys together is V is equal to ED or ER. the differences between these hops is expressed by these equations, and that's how it works out. What I'm trying to show again, and sometimes this happens in an exam or a test that you have to learn off. That's a pain in the arse. Instead of learning them off, if you can start from Coulomb's law, just Coulomb's law, you can see that you just knock off a Q and you get electric field. You knock off an R, you get the voltage. And you can derive what's missing between those two guys as the R, and what's missing between those two guys as the Q. So you can extract a lot of information all from Coulomb's law. That's how class that law is. Anyways, why did I spend so much time teaching you about voltage and the electric field? Well, because we're coming into part 3 of my front page segment, which is great. We're 4 hours into the stream. My timing is getting really, really well. Part 3 is the third scientist we're going to cover. We covered Robert Boyle from Waterford. The second guy we covered is George Stoney from Offaly. And so now we're going to cover Ernest Walton, his good old friend Cockcroft. And here we're finally hitting people who won the Nobel Prize in physics. Ugh, let me sit down. Obviously, I'm saving the best for last. Kathleen Longsdale is going to be the last person we're going to talk to. She's class. I just want to check the birthday of Walton. Birth location. Ernest Walton. There you go. What county was he born? I think it was Dublin. Was born in County. Place of birth, Dungar. Up Waterford, we have a second Waterfordian. Who knew? Who freaking knew? All right. Welcome in. Emantix, thank you so much for your prime. That's very, very kind supporting the channel. Happy St. Patrick's Day. Yes, so for St. Patrick's Day, we covered Boyle, we covered Stoney, who named the electron. So we have Waterford, Offaly, and now we have Waterford again. So Walton, Ernest Walton, was a Waterfordian. Do I have notes on him? I hope I do. Grab this. I have notes. Isothermal quasi-static. Impedance. Shit. I have nothing on Walton. What? I think it's because I read a lot about him and I thought I'd know it off. But now that I'm in the moment, I have no idea what I'm talking about. Nobody panic. Okay. So Ernest Thomas Sinton Walton was born in 1903 and passed away in 1995. So he lived quite a good long life, and he shared the Nobel Prize in 1951 with his collaborator, with his colleague Cockcroft. Anjay, thank you so much for the prime. Oh, sorry, for the sub even. Wait, it is prime. My precious is prime. Yes, thank you so much for your prime. Really appreciate it. Welcome in. He shared the Nobel Prize with John Cockcroft for the pioneering work on the transmutation of an atomic nuclei by artificially accelerated atom particles. What that means is that they grabbed an atom, a lithium atom specifically. And if I remember correctly, you can correct me on this chat if you want, it was lithium-7, which meant that it had 3 protons and 4 neutrons. And they bombarded it with a proton. There's an alpha part. I might be wrong about this. Let me think about it in a sec. He bombarded it with a proton. And what did he do? He split the lithium atom. And he split it and he made 2 alpha particles out of this. I could be wrong. I might need to be corrected on that. Let me know. This is why I should have made notes. I made notes on everyone except Walton. I apologize about that. It was lithium-7. Okay, thank you. Thank you for confirming. Again, I'm winging it. At the moment, I'm winging it. So even though he was born in Dungarvan, in Waterford, he moved to Limerick for a good amount of time and then into County Monaghan. So he actually travelled all over Ireland. There's some Limerick representation, there's some Monaghan representation, but ultimately he obviously went to university in Trinity College Dublin. Very famous university in Ireland. I guess it's the most prestigious university in Ireland, I think. I could be corrected on that. You guys let me know. What's really, really cool about him is that he got a fellowship award and was accepted as a research student in Trinity College, Cambridge, under the supervision of the one, the only that we mentioned a little while ago, Rutherford, Ernest Rutherford. So to shout out to any of the New Zealanders in the chat who are staying up very, very late to watch the stream, representing one of your own in here. So during the early 1930s, Walton and Cockcroft built a really, really cool apparatus. I'd love to show you the diagram. I was thinking about building this on stream, but I don't have an AC signal to do it. So unfortunately, I can't build this machine on stream, but it's really, really cool. I taught you recently about capacitors. So there's a bunch of capacitors, a bunch of diodes in a really interesting structure, sometimes referred as the Walton-Cockcroft structure, of amplifying an AC signal into a really, really large DC signal to make a particle accelerator, because there's all these issues that happen with degradation around electricity and components to make a really big potential or to create a huge electric field. It was like 700 kilovolts. That's how massive the potential was. The splitting of the lithium nuclei produced helium nuclei. They went on to use boron and carbon for their disintegration experiments, and it induced radioactivity. So this was really, really important moment. So the experiments proved the structure, the atomic structure that was proposed by Rutherford. We know that guy. And another guy called Gamow. He's a Ukrainian. I'm not sure how to pronounce it because it's Gamow. He's really, really famous as well. Really, really cool dude that I talk about when we talk about the creation of the universe. He had a lot of work around that realm as well. So obviously they built the first particle accelerator called the Cockcroft-Walton generator. It is in a museum now, I think in Cambridge or around the area of Cambridge. And they won the Nobel Prize in 1951. So how old was he when he won the Nobel Prize? He was 46 years old. I have some time. I have some time left, chat. One day we will win the Nobel Prize. Perhaps. Alright. And so that is a little brief history on Walton. He continued to... He got some tenureship in Trinity College Dublin, I believe, and he donated his Nobel Prize medal to Trinity College Dublin, I believe. So yeah. Gamow. I thought it was a V, but for some reason, when I saw the spelling, it was with the W lint, and I thought that was a bit weird. I always thought it was Gamow. It is what it is, I suppose. You can win it before you are dead. Yes, I must win it before I die. There's only so much time left. We're racing against the clock. Okay, so that is everything that we want to introduce about Walton. And what we're going to do is we're going to do a little bit of transmutation physics. So the word transmutation I want to know, is it Greek or Latin? No. I know what it means. I need the etymology. There we go. There we go. It comes from Latin, okay, for to change from one form to another. So trans is across and beyond, and mutare to change. So there we go. So what we're basically doing is we're grabbing an atom. We grab an atom with protons and neutrons, and we change what the atom is. So we're going to cover a little bit of atomic theory with you. Looking at the time, how am I on time? I take a break now before we start covering? It might be a better thing to come in. I know the break is a bit early, but we'll cover everything on the board then. Hi, John. Welcome in. Oh no, I'm getting A-level chemistry from. Sorry. Lead into gold. Exactly. So we're basically doing alchemy. No, you're absolutely right, Shattered Phoenix. This is proper physics alchemy that we're doing. So what we're going to do is we're going to grab an atom and we're going to bully it. We're going to beat it really hard and really fast with another atom. We're going to split it. That's it. Another thing that wasn't mentioned, I could be wrong, chime in if you guys know better than me. This was also the proof, because they measured the energy released during the collision, that they also measured and predicted or confirmed E is equal to mc squared. I could be wrong about that. I'm happy to be corrected, but so what I might do, I know it's a bit early, the ad break isn't over yet, but I might go for a quick break here. So when we come back, we're going to do transmutation physics. I need to grab my textbook anyway, because I'm going to reference a textbook for this one. Yeah. We can take our time with this, because for the diffraction grating experiment, it's a pure experiment we're going to do on the brain. We're just going to do some science, a real experiment. I never heard of fission as atomic bullying before. I mean, what else is it? You're beating up an atom. Rude. I mean, okay, I'm going to say something a bit weird here. We haven't covered it yet, but in radioactivity, when things undergo natural transmutation, we call the parents as parents and they become grandparents, and we call the nuclei that they produce as daughter nuclei. So if you look at it, it's basically forced child reproduction. If you're using a particle accelerator and splitting an atom. Because if that's what you use in radioactivity physics, and you call them your daughter nuclei that you produce, and you force that reaction to occur then instead, this is TOS. We're going to be careful from here on in. All right, everybody, take a quick break, and we'll be back in a little while. Where there is a vacuum. If you create a vacuum, a very thin vacuum, conduction cannot occur because there are no particles to vibrate from one to the next, and convection cannot occur where a particle gets heated up and travels through air. On the outside of that vacuum, we have a silver shiny surface. Basically, we're trying to get it far away from a black body as much as possible, and usually the polar opposite of it is a shiny silver surface. This usually reduces the absorption and the emission via radiation. While a liquid nitrogen dewar operates to keep liquid nitrogen super cold, the same idea works with a thermos that is trying to keep your coffee hot inside. It doesn't matter if it's a really cold thing inside or a really hot thing inside. It is basically trying to isolate whatever temperature it is that you have inside. I hope you found that educational. What do you think, Bambi? Sound can be intense. I apologize for alarming you. I hope your ears are perked. Okay, I'll stop. Let's cover sound intensity, the decibel scale. When we study Introduction to Physics, we talk about sound being a form of energy. Specifically, we tend to measure it in terms of intensity. It's the amount of energy per second being displaced upon 1 meter squared. Hence the unit being watt per meter squared. But we want a number that is easy to reference very soft sounds, like rustling leaves in the wind. We also want it to be able to measure loud sounds, such as jet airplanes and shotguns. And so we have a logarithmic scale for human numbers, where 30-40 decibels is quiet, rustling leaves, and all the way over 150 decibels is really loud sounds, like jet airplanes, guns. The expression is beta, which is decibel, is equal to 10 log
times the intensity of the sound that we're measuring over the threshold of hearing. The threshold of hearing is the minimum sound a human can hear, which is usually 10 to the minus 12 watts per meter squared. We like to use the decibel scale, especially when we're conversing normally with humans, because it's a number that means something instantly. If we're talking about intensity of sound in casual conversation, we'd be talking about units such as 10 to the minus 12, 10 to the minus 9, 10 to the minus 5, and those numbers don't mean much to people in the general public space. Although this equation seems straightforward, how would you solve it working a little bit backwards? So here's a typical problem. Imagine my classroom is operating at 75 decibels. What is the intensity of the sound in the room? 10 is just a number, it's just being multiplied on one side, so to move it to the other side, we're going to divide it. And to get rid of the log, we put everything to the power of 10. The side of the equation that has the log, it just disappears. But the side of the equation that doesn't have the log is put to the power of. In our case, that is 10 to the power of beta over 10. Rearrange the equation to find I on its own, and we have all the numbers. We have what the threshold of hearing is. We know that the decibel is 75, and 10 is just a number. Multiply them all out, and voila. The intensity of the room is 3.2 by 10 to the minus 5 watts per meter squared. As you can see, that was a mouthful of a sentence to say. And that is why we tend to not use intensity to measure sound when we're conversing in everyday language. Decibels is a little bit easier to talk about. Happy sounding.
What does the sun, Chernobyl, and a banana have in common? I know they don't walk into a bar. All of these things have radioactive properties, and I just want to talk a little bit about radioactive units. The reason I wanted to do this video is because there's so many, and I didn't realize just how many there are. The first one we're going to talk about is Becquerel. You might know him because he did win a Nobel Prize alongside Pierre and Marie Sklodowska-Curie. The unit Becquerel describes the disintegration that occurs per second. Multiply that number by 37 billion and you have the Curie. This is the conventional unit of activity. Another unit associated with radioactivity is Gray. It is described as the absorption per matter. So the unit would be joule per kilogram. This would be a very important aspect in medicine, for example. Another form of this unit is rad. You probably encountered this if you played Fallout. 1 rad is equal to 0.01 Gray. That is how the rad... I'm back. Right. Perfect. Ads just finished. Excellent, excellent. Hopefully we're ready to buckle up and get into some new science, new stuff. So, what we're going to do is we're going to start talking about transmutation. And I forgot to bring the physics book. Goddamn reason I went for a break. Oh, finally got back. I'm back again. Here we go. Let's open this up. Yeah, there we go. Nuclear physics. Perfect. So, I'm preparing my laser goggles. These are going to be goggles I'm going to wear on stream today. I'm sure Medjay is going to be delighted to see more artwork, or inspired artwork. So, what we're going to do, that's part 2, that's the last part of our demo for today. But for this part, we're going to cover some nuclear physics. So let me pick you up, chat, again, if you guys are all right with it. Come here. Come here. Who's ready for some upsies? Here we go. Up, guys. Oh, there. Perfect, perfect, perfect. Here. Earth. Alrighty then. All right. Now, let's talk about transmutation physics. Really, really cool. What we're basically doing is we are, what's the word? We are changing atoms. So thanks to Cockcroft and Walton, the Irish physicist from Waterford again, we were able to do the first time an actual real transmutation, as in like atoms decay. They do it naturally via radioactivity. There's alpha, beta, and gamma decay. But this was the first one where we forced it to happen. And so I think I have even the reaction to show you exactly what happened. Maybe I'm wrong about that. Maybe I'm not. This is some form of it, okay? Where we had a lithium atom with, the element is, by the way, 3 protons. And then the atomic number is 7. I'll explain all of this. I'm just giving you an example first. Changed, for that. And they bombarded it with a proton. Drew helium-11 is another way of writing it. And you got 2 helium atoms out of it. Whether or not this was the exact situation that happened, it doesn't matter. What I'm just trying to show you is a proper example, okay? So, what does all this mean, though? So what? Topher wrote this equation up on the board. I don't even understand, what's going on. What's the story here? So, the number that's here on the lowercase, I want to make sure I'm doing this right. Yes. The number that's below the element name is the amount of protons that are present. What does that mean? So remember when we said that there's a bunch of protons inside the nucleus of the atom, like this, and then there were orbiting electrons around it. There's electron here, electron here, electron here, and electron here. Woo! They're having a great time orbiting all around. Excellent. But there's another thing inside the atom. And the other thing inside the atom are neutrons. These neutrons add weight to the atom. It's heavier if it has more neutrons, but it doesn't change what the atom is. What defines an atom? What defines an element? What defines, for example, how do we know that lithium is lithium? How do we know that copper is copper? How do we know that tungsten is tungsten? And so on and so forth. How do we know that? It's the exact amount of protons inside their nucleus. So if it has 3 protons inside of its nucleus, it's lithium. You can grab a periodic table and have a quick look at it. If it has 2 protons, it's helium. If it is boron, it has 4. I'm trying to remember. I'm getting mixed up between my oxygen and carbon. It's not 12. It's carbon 12. So 6, right? And so on and so forth. I think beryllium is 4. Is it beryllium? I thought it was boron. Oh my god. Is boron 5? Beryllium, boron? We'll take it. You guys can open up the periodic table and confirm or deny all the rumors I'm spreading. It is, yeah. Perfect. All right, there we go. Basically, the number of protons inside the atom define whether or not define what element it is. So that's what the periodic table is. You add 1 proton, you have a new element. You add another proton, you add a new element. So in case you're wondering, like, how are they discovering new elements? And what does that mean they predict an element exists? Well, because all you have to do is add another proton. It's not just that, by the way. It's actually really, really difficult because it has to exist for a certain amount of time, and there's a little, the strong nuclear force, electrostatics, and all of that stuff gets a bit problematic. But generally speaking, you add a proton, you have a new atom. It's great. So you don't have to match it though. Most of the time, most atoms do. Well, no, the bigger the atom it gets, the more neutrons, because you need a bit more space usually. But the more atoms that you have, or the more protons that you have, generally speaking, the more neutrons that you have. And they're usually in equilibrium. 4 neutrons and 4 protons. So if I had a lithium ion, a lithium molecule, I would have 3 protons. That's my atomic number. And then my isotope number, element, no, what's this term called? This textbook tell me what it is. Mass number? I guess mass number. Okay. Mass number determines what the total amount of the nucleus it weighs. So that would be all the protons added with all the neutrons. So 6 means there's 3 neutrons and 3 protons. So look at that equation there that we showed earlier. Yes, 7. What does that mean? Chat a fact check. Oh, absolutely. It's very rare. These lecture moments, sure, I teach, but I get loads of things wrong all the time. Exactly. It means 7 minus 3. It means that there's 3 protons in the lithium, but it means there's 4 neutrons inside it. So this is what it would look like. 3 protons. The element is lithium. But 1, 2, 3, 4 neutrons. 4 plus 3 is 7. That's its atomic weight. Okay, so it weighs of 3 of these guys because they're almost the same weight. They're not exactly the same. There is a bit of a denture, but you can add them all up together. Now, a proton, another way of drawing a proton or writing a proton is we can draw H, 1, 1. That means there's 1 proton in a hydrogen atom with no neutrons. That's something that some people tend to do. And think about it. Laws of physics have to apply here, chat. Energy cannot be created or destroyed, but can transfer from one from another. If we put mass into it and we get mass out of it and all these kind of things, the total number of protons and neutrons has to stay the same in these reactions. So that means we have 4 protons, so we're going to have to get 4 protons out. And we have the atomic mass to be 8, so we still have to have 8 in the atomic mass. Would you look at that? When we get 2 helium atoms, 2 protons in the side, another 2 protons inside. 2 plus 2 is 4. It does equal to it. And 7 plus 7 is 8. 4 plus 4 is 8. So even though we've created new matter, the number of protons and the number of neutrons stay the same. Thank you, Kane, for jumping in. Conservation of mass. Very, very important here. So this is the birth of nuclear physics. This is the birth of man-induced transmutation. This can happen naturally. Helium can be evicted off the surface of elements because of radioactivity. That's what radioactivity is. But if we force it, we can have these things in particle accelerators, just like Walton and Cockcroft did in their first experiment, which they won their Nobel Prize for in 1950. Yeah, absolutely. They could be not the same. But certain atoms are more favorable in terms of structure than others, Roba. So that means that, well, I could have made, I don't know, I could have made lithium 6,3 plus hydrogen 1, 2, or helium 2, 3 and helium 2, 5, or something like that. But you're going to notice that this helium 2, 4 is very favorable. A good atom. Helium's good. Very, very good. I like it this way. So what I might do is I might have a bit of fun with you. And I might put up an equation for you to solve yourselves. Just for a minute to try and solve yourself. To challenge yourself. Here we go. Welcome in, Sister Scone. Happy to have yous. Thank you, Beauty. Okay, here we go. Pop quiz, exactly. There's a pop quiz right now. Let's practice this. If I grab
Ooh, this is interesting. This might be a bit challenging, but let's think about this. If we grab beryllium. Okay, here we go. We have beryllium. We just reached 4,000 followers. That's awesome. If we grab beryllium, and I say that its atomic weight is 9 and its atomic number is 4. Okay, makes sense. Beryllium has to be 4. That's the rule. And I bombard it, and we have helium. Helium 4-2. What if it produced a neutron? It has no atomic number. A neutron does not have any proteins in there. Protons, not proteins. It has no protons in there. What is the element that we created? I'm going to give you guys a moment to challenge yourselves if you guys are interested. Let me just duck down so you guys check it out. I have a few interesting shouts there. Excellent. Do I have the answer? No, I don't. Okay, but that's okay. We'll figure it out. Yeah, there is a bit of Skyrim music in the background. So 9 plus 4... we'll do this guy first. So 4 plus 2 is 6. It has to be equal on the opposite side as well. It's 0 here, so the atomic number has to be 6. Embarrassed here. I'm going to assume that's carbon. And then 9 plus 4 is 13. We have 1 already, so 13 minus 1 is 12. This is carbon 12. The amount we define of Avogadro's number, 6.022, is the amount of molecules found in this exact guy. So carbon 12. Is there now... no. I think this is actually the correct form, but it doesn't matter. But left and right. The notation is, as long as you understand, it's the top and bottom that we just need to be careful of. Top and bottom isn't important. Left and right, I don't think it really matters. I think this is what it is in my textbook at the moment, but again, doesn't matter in which way to put it. That's much. Exactly. It's actually quite. We're studying nuclear physics, but it's not too crazy. Okay, will I challenge you one more time, or are you happy? Do you want to move on? Maybe we'll challenge one more time. Let me see if there's anything in this one. Actually, let me pull up a periodic table. This could be fun. Table, here we go. Have a quick look here. So, what if I grab magnesium? What element is it? 12. Make it 25. And we bombard it with boron. Boron 5. 10. There we go. All right. And out of that, you get helium 2. Ooh, interesting. Solve that one for me. Have a periodic table open for yourselves. There you go. Give you a moment. Wolfgang Pauli is really, really cool. Also, just an amazing name. Okay, well, let's just do the maths. We might not know the element, but we can look it up. Let's do the maths. 12 plus 5 is 17, so that's how many protons we have. 17 minus 2 is 15. The element number must be 15. Okay, whatever element that is. We'll look it up in a second.
But let's check how many neutrons we have. So it's 25 plus 10 neutrons and protons. 25 plus 10, which is 35, minus 2. Wait, what did I just say? 35 minus 2, which is 33. We must have 33 left over. So let's look up periodic table of elements, and let's look up what element 33 is. The 33? Sorry, element 15, not 33. And 15 is phosphorus. The symbol for phosphorus is P. And we have made phosphorus. So it's a bit confusing to keep track of them. That's okay, but it is very interesting. Now, while arsenic is 35, yeah. While we're on the topic of phosphorus, and while we're on the front page, story time. Get cozy, chat. Let's fix the mic here. I didn't realize I was so quiet. Apologies. Let's get all nice and cozy. Yeah. My helium has no neutrons. It's an alpha particle. Helium is just 2 alphas and no... sorry, it's not even a helium particle. Sorry, it's not even an alpha particle. It has no neutrons in there. So that's weird. It's just 2 protons stuck together. I don't know if that exists, actually. Does it? Can 2 protons exist without neutrons? You guys confirm or deny? I wouldn't know. Ready for story time. Yes, so members of my community know the story. This is a great story. Without neutrons, yeah. Boomcake jumps in to say they cannot. I'll take your word for it. Story time. So how was phosphorus discovered? We're going to go into the history of alchemy, but back in the days when it was actually called alchemy. This is great with a skull. We have a bit of an ambiance. And so we're going to talk about Brand. And so what Brand did was that he did an amazing distillation and fermentation process of pea. So he grabbed pea, he would distill it or ferment it first, then distill it, do all of these different processes until he could extract a glowing little material in hopes of finding the Philosopher's Stone, and so named this glowing liquid that he was able to extract as phosphorus. He continued to do his scientific experimentation by collecting pea from his local pub. He would grab buckets and buckets of pea of strangers' pea from the local pub, put them into his house, and allow it to ferment for days and weeks at a time. He would then continue some process of distillation, condensation, a few other bits and pieces to finally extract that glowing phosphorus that he kept the recipe for a secret. And you might wonder, where did he get all this money from? And I always give this advice to my lab rats. He married a rich widow who funded everything for him. So there is your goal in life. Marry someone rich so that they will fund your pea research. If that's not a noteworthy story from the front page, I don't know what is. Isn't that right, Jeremy? Oh, let's put you back down. Red card. Well, that's the stories. That's the stories. I've said it a few times to my own community. They're very aware of it. But we have many welcome new members. Words of wisdom. Oh no, Archseer. Okay. Oh, I dropped my stuff. Ow. Anyway, sure. Marry rich, exactly, marry rich. That's what I need to do, marry rich, so that I can get funding for my research. It's tough these days, lads. It's tough these days to get research funding. Well, now we know what we need to do. Now we know what we need to do. I don't think it's atomic physics what I want to do. I think it's nuclear physics that I want to do. What chapter is nuclear? Like, I wonder, should we do some E is equal to MC squared calculations? Because that could be fun. As long as it's not too difficult.
Back on the menu, boy.
Thank you, Archseer. Celebrating the Irish physicist, Tiny Toxic Tofu. Thank you, thank you. You're very kind. Very kind indeed. Ah, there we go. It's the last chapter. I married him for physics. Here we go, nuclear physics. Do I want to do some MC squared calculations? No, that's the delta M values of them. That's the transmutation stuff. Do you know what? There's a really interesting radiation, a fission problem of uranium-235. And it's a little bit of E is equal to MC squared stuff. It's very nice and basic. We haven't, gone through it too much. But I think it might be fun to cover. Even though we maybe didn't, do things properly with it. Yeah. Because we need to, do a lot of stuff on radioactivity, but that's not the topic of today's segment. So just bear with me, sorry, is the proper figure of speech. Just bear with me. We'll cover a few bits and pieces. I'll do this exact problem here. Oops. Forward. Up. So, we have an interesting problem. A question, I don't know, how do you know that MG and B... Oh, I don't. In fact, this is not even possible technically. I was just kind of showing a mathematical process of how to add those protons and those neutrons and how to keep track of the atomic number and so on and so forth. It was just a mathematical example. Does that make sense, Holy Dancer? It wasn't like a proper reaction. The first two were proper reactions. But how do we know which one is going to happen now? Well, because a lot of experimentations have been done on this. The idea behind it is that you can predict which atoms are way more stable than others. You can see by their energy what keeps things together. And you can predict the atoms that will be made because certain atoms or certain atoms, certain elements are way more stable than others. And you'll notice that a really fun thing with the Big Bang Theory and so on and so forth is that there's a very, very stable atom that everyone wants to hang out with. Iron. Everyone wants to be iron. Iron is great. And so everyone strives to be iron, whether to transmutate by getting heavier or transmutate by getting lighter. But it's not a perfect line. Some atoms in between are better than others, so they kind of tend to go backwards. Helium, H42, is a very good atom. For how small it is very good. It is very good indeed. All right. So here's a problem, chat. It's a bit out there, so don't worry if this is a bit difficult. When uranium... 5. The famous ones that we know about is 235 and 238. I don't remember which one is for fission and which one is the bad stuff. Always forget. Chat can confirm or deny the rumors we're spreading. Has 92 protons in there. That's a lot of protons. It'll take you a long time to draw that out. There's 92 protons and about 0.1%. About 0.1% of this uranium of the original mass is released as energy. So as it's radioactive, as it radiates energy via alpha, beta, gamma particles, 0.1% of it of its original mass is released as energy. Okay, kind of think about E is equal to MC squared. Number one,
much energy is released? Okay, that's exactly how we can calculate it. If we have 1 kilogram, if I have 1 kg uranium in my hand, probably shouldn't have that, but let's say for argument's sake, I'm holding uranium-235 in my hand, about 1 kilogram of it, and about 0.1% of its mass is released as pure energy. How much is that? So how would you calculate it? Well, Einstein's famous equation, E is equal to mc squared. We're not going to be using the relativistic version of it. Grab whatever mass that is. 0.1% of 1 kilogram? That's 0.001 kilogram. Yeah. Is there another 0 in there? 1% be 10 grams, right? Yeah. Yeah. Double check that I'm right, that's 0.1, just in case. And speed of light is 3 by 10 to the power of 8, all to be squared. So how much energy is released from the uranium? So that is 3 by 10 to the power of 8 to be squared, all multiplied by 0.020. That is 9 by 10 to the power of 13 joules. Joy. Holy smokes. That's a lot of energy. 0.1% of its mass is changed into energy. It's 1 kilogram of uranium in my... That's a lot. That's crazy, no? Okay, well, it is. It is what it is. This is the power of E is equal to mc squared. The amount of energy being released by material is insane. Well, another thing that we can calculate, the question says, how much of this uranium must undergo fission per day in a nuclear reactor to provide 100 megawatts? So we want to change the mass of uranium into pure energy. How much of that do we need to operate at 100 megawatts? 100 megawatts isn't that big. Maybe for 1 kilogram uranium it is. But just to kind of estimate roughly, a big giant coal generator is about 300 megawatts. Okay. Well, hopefully we're aware of power is equal to energy over time. So energy is equal to power times time. Hopefully we're aware of that equation. Welcome in, guys. So we say that the generator is 100 megawatts. Mega means 10 to the power of 6. And time, well, in a day. So 24 hours in a day multiplied by 60 minutes in an hour multiplied by 60 seconds in a minute. Convert it into seconds. So that is 100 by 10 to the power of 6, all multiplied by 24, multiplied by 60, multiplied by 60. There we go. That is 8.64 by 10 to the power of 12 joules. Raise this meter in joules. That's a lot. That's a lot. That's a lot. And so the question asks, well, how much of the uranium must undergo fission per day? So we know that this is what's produced when 0.1% of the mass changes, which is what? 1 gram? Yeah, 1 gram of uranium is equal to 9 by 10 to the power of 13. So let's divide that by that number. 9 by 10 to the power of 13. Did I do that right? Hope I did that right.
Oh, yes, because it's going to be in kilograms. That's fine. I was worried about my units there for a second. I said grams, but we did this everything in kilograms earlier, so everything's fine. So what we're going to do is 8.64 by 10 to the power of 12, all divided by, in your brackets, keep track of that, 9 by 10 to the power of 13. Go, close brackets. And so it's 0.096 kilograms or grams. So you need 96 grams of uranium to produce a 100 megawatts of energy per day. That's not a lot. 100 grams? Sure, that's just not even a cup of flour. Totally easy to do, chat. Whoa! But this is a little interesting. So 3 grams is equal to 300. Yeah, exactly. So roughly 1 coal plant. Exactly. But nuclear stations, one of the, it's not called a turbine. I always forget what it's called. You know, one of the chimneys. It's called a nuclear section. I don't know how to call it. It has usually four of those tubes around. Not smokestack, the reactor. Thank you. Oh, for feck's sakes, my brain sometimes. The reactor. So there's several reactors usually. I think one reactor, correct me on this, can produce 1,000 megawatts. Nothing can produce that amount of energy. Nothing can compare to nuclear power in that amount. Oh, except for, oh yeah, I mean on Earth. In terms of our ability to harvest energy is probably the better way of phrasing it there. So yeah. I mean, it's theoretically possible, sure. But to make it possible, yeah, I'm not sure. Yeah, and it's used to heat energy to make a turbine go whoosh. Basically, this, I'll show it to you now. This is how we power our world. This is how it all works. This, how I'm able to turn on my PC and to stream to all of you around the world on St. Patrick's Day. Here we go. Have a little motor, some magnets, some brushes, and you either create steam to make this go in a circle, or you have a wind turbine and you can blow it. You get power, you get light, you get electricity. So that is how our whole world functions. Exactly 100 plus years later, we're still using steam. We're still using the ability to rotate things, yeah. It all boils into steam. Urishka. Well, the one thing, like for example, that we don't do, solar panels don't heat things. That's one way of energy of us getting direct power. Problem is it's DC. So we have to do AC conversion with it. So that's its biggest issue. I don't know how big of an issue it is, but yeah, there's a lot of discussion about that for sure. Yeah, solar in New Zealand makes sense. Australia, New Zealand, that's a great way. $158 inverters. Jesus, that's a lot. Yeah, you need really good inverters for sure. And that ends my segment on Walton and Cockcroft. Specifically Walton, obviously an Irish scientist, also from Waterford, which is great, and his work into splitting the atom, into how he got the Nobel Prize for physics, or in physics. He shared it with Cockcroft. They both were given credit to both of those things. Hi, Opinionat. Welcome in. Welcome in. While we're I need a break anyway from the teaching just for a few minutes, just to sit down. I'm just going to move a few things around in preparation for an experiment. Yeah, because we're going to do a fun experiment next. Or at least it's a proper experiment, you know? We did a proper experiment earlier with Boyle. I'm using some of my lab rat passes. That is a great question, and unfortunately I don't have the time to answer it right now, Mystic, but according to Newtonian or classical physics, that is true. Because the electron is emitting electromagnetic radiation, it should, kinetic energy, half mv squared, it should be reducing in speed, v, which means if it's reducing in speed, it wouldn't be in a stable orbit and it would collapse inside the electron. That is where the introduction of quantum physics had to come in, to basically explain that exact problem that you meant. I don't know if that's very helpful, but the summary is that's why quantum was invented. Quantum mechanics had to be invented to explain that exact problem that you mentioned. And that's when the world went to shit. Okay. Am I late for the lesson? So we're starting the 4th lesson of the day. So we did our first 3 lessons. We did electric fields, we did Boyle's law and the ideal gas law, and we did particle physics or nuclear physics. So now what we're moving on to is some diffraction stuff. And this one is going to be an experiment. I'm okay. I just got scared. What else? Maybe I need a power cable extension. Cool stuff here. I'm so glad this channel exists. Oh, thank you. I'm glad that a lot of you have been able to find me on Twitch. Really appreciate that you guys are interested in this. I don't stream very often, like I said. I am a full-time physicist out there in the world, so you'll see me this weekend. I'll be around this weekend. Sometimes I'd have to take a few weeks of breaks. Three Gorge Dam in China is the largest power plant in the world, and it uses 32 turbines for a capacity of 22,500 megawatts. Class. So was that a rough estimation that 4 turbines produce one? Did I get that right? Is that simultaneous, or if they were all? Because most turbines don't operate all simultaneously. I suppose we need to read the fine print, but still, that's really, really cool. Yeah, China does amazing stuff. So all the largest, the 2, by the way, largest vanadium flow battery systems are actually both in China as well. So it's really, really cool. And a lot of researchers in vanadium flow battery at the moment in publications are from Chinese authors. Some really awesome research is being done. Research in the name of science. And it's really great to see someone like me who's doing theoretical work is being used in real stuff, you know? I don't know about you, but I think that's pretty cool. Pretty cool. As they say, theory will only get you so far. And there's a lot of like notions or how should I say it?
Call it
A lot of people can be
mine.
quite pessimistic
A mine.
about academic research because there's no application to it, and I will argue all the time against that anyway, but I personally even see it at the forefront that it is being useful. Seattle Green, thank you so much for the sub. You're really, really kind. 5 months in a row. Let's go. Thank you for the sub. For the paper points. So I'll be the laser. I'll set the camera a bit better. I need an extension cord, I think, to make this. I have to be careful unplugging any apps though. Because if I unplug it, my PC is going to shut down. That'll be the end of us. Happy Physicist Day. Happy Irish Physicist Day. Where's my other plug? It's over there, isn't it? That's that. Everything is plugged out for... I can plug an extension over there, I think. Here. The laser's probably very... Is that high powered? What's the wattage on this? Go? Nope. I mean, it doesn't matter. I know I can plug it in, but, you know, plug it into extension cords and all that. Electro Boom collab, please. Oh, goodness, no. Goodness, no. Use a quantum plug. Oh, well, the problem with my quantum plug is I'll never know where it is, you know? You aimed it right at us. Don't worry, don't worry. It's not plugged in. Everything's fine. Everything's fine. So what I might do is we'll talk about the last section of the stream that I've planned today. We'll start with the history, a little story time. And then when I come back after the break, I'll have the extension cable and everything. And we will do a real experiment. I've set it up here already. So let's talk about probably the person I saved for last for best. Best for last. And the person we're going to talk about is Kathleen Longsdale. So, Kathleen Longsdale, I have a few notes on her, was always a high achiever when she was young in school. So this is, so she was an adult during World War II, and she was a child during World War I. So have a rough estimate of what age she is if you need to know that. So she was really, really good at maths, really, really good at physics, so much so that she was put into an all-boys school in secondary school because there wasn't the maths and science being taught in those schools at the time. And so she went to an all-boys school around the age of, again, high school level, so anywhere between 14 to 18, and she was studying there. And yeah, she entered many, she did a degree in mathematics. She entered a few scholarships. She was awarded at, I'm going to be jumping between University of London and Leeds. Those are the two universities she was associated with. She moved from Ireland to England during this time. And she applied for a scholarship, received a scholarship in her University of London, and she graduated the highest mark of her year, number one, but number two, the highest mark ever achieved in 10 years in the University of London in that whole degree, in that maths degree. So it was incredible of her time. And the Nobel Prize winner Bragg, B-R-A-G-G, discovered her via this and spotted her and asked her to join her research team. Now, she did a degree in mathematics, but this was chemistry. So she joined his research team into studying molecules using X-ray diffraction, and we'll cover that in a little while. Well, light diffracts. You put a bin of splits, light diffracts. Instead of using light, use X-ray. There you go. Explained it really, really quickly. And she spent her master's and her PhD research in studying the diffraction, X-ray diffraction of crystals of organic compounds. And that's where she got her master's and her PhD. She then married her husband, Thomas Lonsdale, and he encouraged her to do her research. So that was quite novel at the time. I'd love to do a series on this, on Maria Sklodowska-Curie, on Maria Gobert, on Longsdale, that a lot of these women were able to achieve so much in their life. Because, first of all, they're amazing women. But there were loads of amazing women, names that we don't know as much. And all these women, for example, had extremely supportive husbands that pushed them away. For example, Pierre refused to accept the Nobel Prize unless Marie was going to get it. You know, they really stood their ground for the significant other to show that they deserved what they obtained in life. And that's why we know their names now. There are so many people out there that we don't know the names of properly. And I'd like to highlight those husbands. It shows that, you know, this whole push towards feminism and equal rights, it's a dual thing. We have to come together for this. It is not one versus the other. It's teamwork. Yeah, she was made a dame. That's correct. She's Dame Kathleen Longsdale. That's right. So her husband gets hired as a lecturer in
They will go to space preserve.
Hi, Preserve. Exactly, Zozo. She gets hired in the Leeds chemistry department because her husband was hired as a lecturer and he stood his ground and got her a job as a researcher there. Again, we appreciate a gentleman supporting his wife and her career. And that's where she did the coolest thing that she's known for. Okay, hold on to your butts. If there's any chemistry people in the chat or did chemistry, this is kind of like an exciting moment, or this is what it relates to. She published her work and proved something that was only theoretically proposed, that using X-ray diffraction and looked at the crystals of hexamethylbenzene, she proved that the benzene ring is flat. It was only theoretically proposed. It wasn't confirmed. It was just an idea, but using X-ray diffraction, we're going to do laser diffraction later, she was able to prove that it was a flat ring, which is a weird structure. Benzene ring is really, really cool. For any of people who studied organic chemistry, you know that, like, there's a whole freaking field of chemistry dedicated to the benzene ring, pretty much. So it was a really fascinating moment in chemistry. It really revolutionized molecular bonds and structures. Not only that, she became the first female, oh my god, in so many things. She became the first lead of Department of Chemistry in Leeds. She became the first woman, oh my god, I can't even track. She had so many firsts. Another first, and very important, was she was the first woman to be allowed to join the Royal Society of Science. Yeah. It was kind of heartbreaking because there was other women that we know that were very famous and very well able and super smart and super amazing, and they weren't given the chance to enter the Royal Society. It was the first woman that she was allowed to join. She herself and another woman, by the way, they came in at a perfect moment together. In 1966, she also discovered, oh no, not discovered, but in 1966, a rare form of hexagonal diamond was found in meteorites, and they named it after her, not Lonsdalites. So there's a really weird kind of structure that occurs in a hexagonal form in diamonds that is only found in meteorites. You can make it artificially in the lab, but naturally it's only found in meteorites, and they named it after her, that construction. And over the life, she became a committed pacifist. When I was doing this research, they called her a quarker. Now, a quark is a subatomic particle. Does anyone know what that is? I've never heard of it before until I was doing my research. I did my PhD in electrical class. Oh, the synchrotron, really, really cool. No, so I know what a quark is. She was called a quarker, like this. I've never heard of this word before. Yeah. Was it a Quaker? Did I write it down? No, I wrote down quarker. Okay, maybe I spelled it wrong. What does it mean? I've never heard of either of those two words anyway. I'm going to Google it. Oh, it's a religious thing. It's a historically Protestant Christian movement. Religious Society of Friends. Oh, that sounds nice. Ah, okay. Not a quacker. No. Okay, never mind. She was a quaker. I've never heard of it before. That's new to me. Okay, well, that's what she was. She was an extreme pacifist. Because she lived through some really bad trauma during World War One, and she refused to work through when World War Two. It's Quaker. Ah, okay. Okay, Quaker. Oh, maybe okay. Fair enough. She even refused to register for civil duties by principle. Now, she had 2 kids, so she didn't have to join the military in England at the time because she had two kids by then, which, by the way, again, supportive husband. He, cut back on his hours at work to try and take care of the children so she could do research while, even though that structure did not exist. Nowadays, it's a lot more socially acceptable for men to work at home. But this is almost 100 years ago, lads. So, again, I need to do a video series on supportive husbands because those women helped, or those women were able to get recognition thanks to support, and support is so important. Anyways, I'm getting distracted. She refused to register for civil duties by principle. She was fined £2 because she wouldn't register. She went to prison for that. She went to prison for refusing to register for civil duties by sheer principle because of her being a pacifist, and she was sent to prison. She has a criminal record, chat. In 1943, she went to jail. After she went to jail, she became what is it called? A prison reformer. When they see that the prison is in a really bad state and try to get the rights of basically get prison rights elevated and improved and the living conditions improved. Anyways, yes, she became a prison reformer, prison activist. And during World War II, when she got out of prison, she actively was taking in as many German refugees as possible. She was really always trying to push to do good in her life. She did die about 60 years old, so she didn't get to live for a full on not a full life, we'll say. The way, what I say is a full life is, in terms of longevity, is at least the ability to retire for a few years. And the retirement age in Ireland is 67, I think. So if you don't live past age 67, you don't even get to retire. Which is kind of, yeah. Anyways. I turned bleak very, very quickly there. What I like to mention about her, and this is the thing I look up to her the most. First of all, she was a woman of science, a woman of STEM. Her lectures were extraordinarily difficult. She designed lectures on X-ray diffraction. Her whole module was on it. She was the first person to teach it, by the way. I think one of the first anyway. It was one of her many firsts that she did. And it was very, very difficult. She was very kind, as in if you asked her a question, she will sit down, she'd come to it, but it was tough. One of the toughest modules that you could possibly take in the university. But she was also a very able science communicator. She spent a lot of her time when she was young, and in her, actually throughout the years, it was throughout, going around primary and secondary schools to all girls schools, doing science communication and trying to teach girls that it's okay to go into STEM. That's incredible. This is so many years ago. This was before World War II. And she was doing the job that I do, which is, again, so incredible. This was so ahead of her time. This didn't exist before, to go around schools to do science talks. No one really did that, number one. And number two, she was targeting women specifically, young girls. She was extremely ahead of her time with her ability to communicate science and to push the passion of women in STEM. Before it was, a buzzword or not. What was her name? Kathleen Longsdale. So I have her surname typed up in the title. Kathleen with a K. And that is her story. Very incredible woman. And you might say, but Tofu, you're doing physicist. She's chemistry. Listen. Everything is physics. X-ray diffraction is a physics phenomenon. Everything is physics. To me, most of the chemists I know are actually physicists, and they don't know it. They're ashamed to admit it, but you're all physicists, lads. You're all physicists. Exactly. It's all physics. You'd be surprised how many of you guys are sitting at your PCs watching the stream.
And they call it a mine.
You all are physicists. Foghorn, thank you so much for gifting a gift sub. Welcome in, welcome in. I don't know. Yes, he lived longer than her. I know that in her obituary or whatever I read, it said she was, what's the figure of speech in English? She's survived by her husband and 2 kids was written on her obituary thing. So her husband lived longer than her anyways. Oh, that's right. That it was how I think X-ray diffraction was how the double helix was discovered as well, Zier. You're right. Can we just scientists? Sure, sure. I think the word scientist, am I right in saying that, was a name used for female researchers? The word scientist inherently initially was female only associated. I could be wrong about that. He lived longer. That's mathematically... Yeah, button smash. It's unfortunate. She didn't live to retirement age. Maybe the retirement age was different back then. It probably was. But my head at the moment, the retirement age in Ireland is 66, 67 years old. Yeah. Oh, favorite thing about the Spire Daily Can. Oh, I used to be obviously chicken roll, but I think a sausage roll with some rashers. I don't like the full Irish breakfast in a roll. Just sausages and bacon, or rashers, whichever you prefer. It depends which one you go. But yeah, those would be my favorite. Hello, welcome in, Port. So what we're going to do is I'm going to take a quick break. Oh, she died at 67 when the retirement was 60. Okay, fair enough, fair enough. No, but she died in England. She devoted her life to University of Leeds. Leeds University? I don't know what structure of sentence Leeds is. But yeah, her life devotion was to Leeds. She got her education in Cambridge, moved to Leeds. Oh, education in London, University of London, moved to Leeds. So we're going to take a quick break. I'm going to get a power cable, and we're actually going to do some really awesome physics here. And we are going to measure and do some diffraction with the laser, replace the laser with an X-ray, and this is how people like Franklin with the double helix of the DNA, or how Lonsdale showed that the benzene ring was flat. How do they measure molecule sizes? How do they know the structure of the molecules? I'm going to do a full demo and mathematics here on live Twitch. We are going to be using a laser, high-powered laser. So everyone, safety goggles. Make sure you grab your safety goggles. Lab rats. Let's see if this is the right size for me. Looks pretty bad so far though. Ugh. Ugh. I might need to adjust the tightness of this. But yeah, we're going to put on these goggles for safety, health and safety, everything to be TOS compliant. Do I look like a mad scientist yet? I better. Is the rabbit locked out? She is. She is. I think it's all arbitrary, Pratik, if that makes sense.
They call it a mine.
All theoretical physics is applied and all applied is theoretical. I really don't think there's that much distinction between them. And most physicists I know don't really distinct between those two things. There are a very small amount of theoretical physicists, and there's not a whole... I don't know how else to kind of say it, if that makes sense. That I think it was that TV show Big Bang Theory. Sheldon was a theoretical physics, and what the other dude was an experimental physicist. And I always thought that was weird, that was their title. That's not how it's done. It's fields of research. So you could be applied or theoretical or interdisciplinary, but you just name what area you're in. So, you know what I mean? It's not just a blanket statement. Anyways, I'll be back in a little while. Oh, thank you, Anonymous, for gifting Sammy Man. Thank you, sub. That's very, very kind. Leonard, that was the name. Sorry, Hacks. I forget these names. I'm very forgetful of names and labels. Yeah, Slad, I absolutely agree. This is why I keep saying that X-ray diffraction, yes, Longsdale was a chemist, but she was doing pure physics. Everything is physics. That's a bit it sounds like I'm being pretentious, but it's not. The whole world of science, the whole field of science is just divisions and subcategories and models of certain things to work to make things feel better. When are you doing the push-ups? That was an old thing. I don't do push-ups anymore. Anyways, I'll be right back. Bye. 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 Bye.
Actually has really sound theories that have existed for a while. Although sci-fi, I do appreciate the physics-esque aspect in the game, and they really follow water.
Evil? Hi, bees. Welcome in, welcome in. Happy St. Patrick's Day. Welcome in, welcome in. I tied my hair back because we're in the lab. You have to tie your hair in a lab. You have to wear goggles, lab coat. Oh, I have a lab coat upstairs. Yeah. The differences with physics, for sure. I don't like to differentiate between the sciences. Like I said, everything is the same. But in physics, we actually don't tend to wear lab coats. You don't work with anything too dangerous. Not that a lab coat's going to protect you about anything. But it depends. It depends. Okay. Oh, so many things, Frank. So all of physical chemistry is pretty much physics. All of electrochemistry is pretty much physics. They just alter the model of the transfer charges and they don't keep track of more primitive physics because it's easier to do a few switches to notations. Organic is a pure different model. I would definitely think that organic is a pure different model. It'd be very difficult. Spectroscopy, diffraction, all of those things are just pure physics. Yeah. I said once I made a physics quiz and I talked about the discovery of the neutron and someone jumped in and said, well, the neutron has everything to do with chemistry. And it's like, no, we discovered it. The discovery of the neutron was a pure particle and atomic physics thing. It's all the same. It's all the same. This is why chemistry and physics should not be battling against each other. We have to unite together. Chemistry, physics, biology, all the fields of science out there, engineering, we all have to work together and fight those business majors. It's the business major. Right, let's go. Yeah, because a lot of people are always like the social sciences or the arts versus STEM. It's not the social science versus STEM, it's the business people. Anyways. Ugh. Oh. There we go. Okay. Comfort cookie. I'm gonna wear other goggles. These other goggles, just because. Whoops. Just because those goggles, if I put them on, although it looks really, really cool, I actually can't see in them. The problem with them is that they don't fit over my glasses. There we go. Okay, safety done. Ooh, need a bottle of water. So let's turn this guy on and see how we get on. Our laser is pointing this way. Oh. Test that it works. Have a laser. Very good. Excellent. Oh, sorry, 2 seconds. I'm just testing a few things here. But a fraction. Work. Nice. Let's go. Okay. Let me set up the camera now as well. So, don't worry. I'm not targeting at you guys. From a health and safety perspective, you should be all okay. Oops. Lovely waist there, I'm sure. Bring this up a bit. Cool, cool, cool. Focus. Oh. Isn't it focusing? Hello. Oh, that is so cool. It's accidentally focusing on the laser. Oh, that's class. There we go. That is so cool. The camera freaked out. Did you see that? That was really cool. Oh, it's doing it again. All right, fascinating, fascinating stuff. We do have a focusing issue. The laser. But as long as I'm here, I think. Okay, so what I've done is, this is just white pieces of papers, and I've directed a laser. And in front of this laser, I'm going to put this guy in. This is simply diffraction gratings. Now, you don't need to know too much about this. I'm going to teach everything you need to know in a second. We're going to do the experiment. I'm going to grab one of these guys, and you don't know which one it's going to be. Dun, dun, dun. And I'm going to put it in front of the laser. And we're going to take a few measurements. Now, I don't have a pen and paper, so chat, I need you to be my pen and paper. So be ready for this. So, what I need... what I need is my assistant. So this guy is a little retort stand. It's for soldering, but he has little arms. And I'm going to use his little arms to hold up my diffraction grating for me. Oh, that's interesting. With my laser, some of you guys I can see very well. Medjay is really, really bright. Penguin, amazing. But who's that username? Let's see who's... Patrick Zeka, you're invisible to me. Utterly invisible. Yeah, some of you are way more prominent with the laser glasses than others. Okay. So what I'm going to do is I'm going to place a rating in front of. So what's happening is I've placed a little grating in front of the lasers, and it is split off from the centers. This guy here is our maxima. Again, I'll cover this in a little while. This is our maxima. And it splits on, so on and so forth. Now, I can use another one just to show that depending on how much your diffraction grating split, you'll get more or less lines. But notice how bright it is here, and it gets less bright and less bright and less bright. This is on the topic of constructive and destructive interference. The brightest point is always going to be at the center, the maximum one, and it's going to get less and less bright the more outwards we get. Now, I'm going to use this one. We're going to do some science in this case. So what I want you to do is someone take this down in a second. I have brought with me a meter stick and a ruler. So I'm going to measure two things. We're going to have to do some trig here. I'm going to measure the distance from the grating to the sheet. It is 91.5 centimeters. 91.5 centimeters. And another thing we're going to measure, if anyone is familiar with trigonometry, is I want to measure the distance from the center point to the next laser. Okay? accident. This guy, sorry. Oh, no. Oh. Now, there is a small issue. The laser goggles are amazing. They're so amazing, I can't see the lasers. So I'm going to be careful. I'm going to make sure my back is turned away from the laser so I don't hurt myself in any shape, way, or form. But yeah, the lasers are so good. The laser goggles are so good, I don't see the laser point. Okay, 18 centimeters. 18 centimeters. And that is a bit of diffraction physics that we ended up doing. I'm going to turn off the laser. Go. Ooh, it's quite warm. There we go. That was kind of sore. All right. Those are really good laser goggles though. Jeez, I couldn't see anything. 18 centimeters. Perfect. Perfect. Okay. So let me just clean up a little bit here for a sec. Move our little dude here who's holding our diffraction grating. Thank you, little dude. Very helpful. Getting all of that sorted for us. So if anyone's coming into the stream now or has been hanging out all day, this is my usual starting time. On weekends. Ugh. I do like to sleep in on the weekends. Get plenty of rest. Oh. Few bits and pieces. Okay. So what we're going to do now is I'm going to give you the diffraction equation that is used with constructive and destructive type of interference and diffraction when it comes to lasers. So hopefully we're familiar, or some of us are familiar with Young's slit experiment, light is a wave, that good stuff. Here we go. Oh, I've zoomed in. Whoops. Sorry. Go. Better? No. Why are you guys so zoomed in on me? Crazy. Crazy. Clean the board. Where's our spray bottle? Over here. It feels so nice and refreshed when you wake up properly from hibernation. Sounds like a dream. Sounds like a dream. We're just going to clean the board really quickly. We're just going to do some maths. A little bit of maths. So, I'm not going to derive this relationship. It's actually in GSC, or whatever the UK version of their degree is called in school. That's actually part of their Leavenscert, or their graduating degree in high school. The equivalency of high school. Again, I apologize for the terminologies. But this derivation is important. I don't know if we need this derivation in Irish Leavenscert maths. The curriculum has changed in the last few years, so I'm not up to date with the exact derivations that are required anymore. Now, what we did is we had a laser. Beautiful laser. And it goes pew, 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 pew. And then it went through a diffraction grating, which is basically a guy with a whole bunch of slices in it. And then we had the white sheet, if you're looking from top down, of what happened. And we had a really, really, really bright spot here. Super bright. Right in the middle. We had somewhat of a bright spot here. We also had another bright spot here. It was getting less and less bright though. And so on and so forth, away from those points, splitting up the little slices, based on the little slices that are there. GSC, there we go. Thank you very much, Zir, for filling it up. Okay. Looking at this diagram and thinking about what Lonsdale did. Remember, she was able to determine the size of molecules using X-ray diffraction. So if you shine something through something that has lots of spacing, get a pattern to emerge. Well, I worked backwards, but I determine what that spacing exactly is. Replace a few words in there. What if that was a molecule and we shone a light, an X-ray, at that molecule, and the grating, the blockage was the atoms, and we can determine the spacing and the structure of the atom based on the images that were detected on our sensor, on our plane, on our, in our case, sheet of paper. So the equation that we're going to use, I'm just going to make sure I got it right, because here since I did it, n lambda d sine theta, is that the one? Let's see, d sine theta is equal to m. Here we go. D sine theta is equal to n lambda. Okay. So what that means is, using this equation, we can figure out what the spacing of this guy exactly is. Now I just want to make sure I'm using the correct one, like I said. So the slit spacing, yeah, that's right. The diffraction order and the first order is that one. Okay, make sure I'm using it correctly. So in our case, it's the atom, right? We're looking at, inverted commas, we're not really doing the atom, but we're doing, if we were Kathleen Lonsdale, if we're cosplaying as her research, she was looking for this. That spacing between the atoms. Sine theta, when you look at the next constructive point of light being created by the laser, do a little dash line like this. If I was able to draw a straight line, what does that look like a little bit? Well, that's a right angle. It's just trig. All that is a big, long, skinny triangle. And that angle there, theta, that's the guy we're looking for. So using this, we can determine what the angle of diffraction is. N is which order of formation do we have? Because obviously this is N1, this is N2, this is N3. The angle is going to change, so we need to keep track of which one it is. What does lambda stand for? Kind of weird. What is lambda? Wavelength. Wavelength of what though? Whose wavelength? Of the laser, exactly. Lambda meteors and shepherd's pie. Happy St. Patrick's Day, Blower. Welcome in, welcome in. Lambda is the wavelength of the laser source. So I used a red laser. Do I need to know? Let me look at it. Let's say on it. Bum, 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 bum. Doesn't say what the wavelength is on this guy. All right then. It would be nice to get a proper exact answer. Wavelength. So yeah, it can be anywhere between 620 to 690 nanometers. And I don't know exactly, unfortunately. So we're just going to eyeball it in between maybe. Well, no, here it goes. A common red wavelength laser is usually 635 nanometers. Okay, we'll take that. We're going to say lambda is the wavelength of our laser light, and it's 635 nanometers. Nanometers means meters by 10 to the minus 9. Okay. It was probably on the box. Sure. What are we trying to figure out overall? We're looking for D. We're looking for the distance between the plating, or again, when we're cosplaying as Kathleen, we're looking at the distance between atoms. Okay, so when you replace this all system with X-ray diffraction, we're looking at the distance between atoms to see how big or what structure atoms are, or molecules are. Sorry. So we have the wavelength. N, we know it could be first order, second order, third order. I did the first order, so I know that that's equal to 1. D is what we're looking for. Sine theta, though. That's a bit awkward, isn't it? What did I say the distance from here to here was, guys? Was it 91.5 centimeters? Is that correct? Can anyone confirm or deny that that's what we measured earlier? Excellent. And then the distance between this guy and this guy was 18 centimeters, wasn't it? 0.18 meters. So hopefully we're all of recollection of Pythagoras' theorem and sine, coses, and tans. If we're looking for the angle theta here, this is our hypotenuse. This is our adjacent. This is our opposite. We have opposite and adjacent. So that means that the tan of theta is equal to opposite over adjacent. Theta is equal to arctan 0.18 all over 0.915. Okay, let's do our maths. I'm glad to hear that, Gunnar. 0.18. Well, I'm not glad that the teacher didn't explain it well, but maybe it's because you're a willing victim here today. The fact that you willingly came into the stream. So we get an angle of 11.13 degrees. Massive angle, no? Oh, I suppose no. Fine. 11.13 degrees. Okay. I think we can calculate what the diffraction grating is. So let me use a different colored marker. Let's rearrange this equation. D is equal to n lambda sine theta. N is the order of the diffraction that we chose. We chose the first one. Easy peasy. 1 multiplied by 635 by 10 to the minus 9 meters. That's the wavelength of the light that we used. And sine of theta, sine 11.13 degrees. All right, moment of truth. What is the spacing between each line? 635 by 10 to the minus 9, all divided by sine of 11.13. We get an answer of 3.29. By 10 to the minus 6 meters. Jesus. That's tiny. That is that many meters. That many centimeters. That many millimeters. 0.003 millimeters distance between each grating. Did I get the right answer? Where's my grating? Where'd I put it? Chat, where did you take the grating? We need to check our answer. Did we do the maths right? Did the laws of physics get obeyed? Oh, I found it. Here we go. Here we go. Moment of truth. Can you guys see this? I used the middle one. Stop focusing on me. Camera, camera, go away. I used the middle one. 300 lines per millimeter. Hot damn! We got it exact. Well, pretty close anyway. Obviously a bit of rounding. Measuring it quite crudely. Good team, chat. Good team. We did a really, really good job. And that replaced the laser source with an X-ray source and bombard the X-ray through a particle, through a substance, measure the diffraction, or measure the angle, the distance, and so on and so forth of the image that is being formed, and you can measure the size of particles. Size of molecule. The distance between different parts of the molecule. God damn it. Anyways. Excuse me. Finish it all with a sneeze. That's pretty cool though. I'm so glad it worked. I'm gonna be honest, I didn't test this before I did this live on stream. So I'm glad it worked. Pretty incredible. So yeah, well done guys, well done. We did some pretty amazing physics today. We did Boyle's law, we did diffraction physics, and we studied the history of 4 famous Irish scientists. I don't know, it seemed quite credible to me. Oh, I haven't, to be honest, I haven't taught this in years. I was really winging it today, in the sense of I took an idea. Nate actually suggested it originally to me, and I thought that was a great idea. Let's see if it works. I hoped that physics was going to be on my side today and it would have worked out. But you never know with these things. You never know with these things at all. Ooh, let me put that away. What time is it? It is now 2 p.m. So this is the time I would stream usually on weekends. I would make a cup of tea or a cup of coffee and we would boot up the PC and start our physics lessons. Great idea, or grating idea. What I might do for a little while is, a 0.033 millimeter. It's even, holy smokes, we got it exact. Well, not exact, but we got it way closer, Hanjay. It's 0.0333. That's pretty damn cool. It was way better than I thought. Excellent, excellent stuff. Great to hear that. Rathania. To be fair, I don't know if it's fair to say that everyone here in this community, in this community, sure, but I don't think it's fair to say that every viewer here is willingly or voluntarily learning something. We're on the front page today, so that means our viewership is extremely elevated, and there's a lot of people here, perhaps against their will, learning physics. Forced learning, exactly. Did you mention the wattage of your... No, and I was wondering about it because I wanted to know like what the laser is. And I couldn't find it. Herder, thank you so much for gifting 10 More lab rats, more victims. Don't look at the skull. That's not what happens to you guys if you stay in this lab, I promise. Thank you, Herder, for your kind support. Very, very appreciative. I am very appreciative of that support. Let me give you some upsies, chat. Guys down. There we go. Okay, here we go. We'll do a little bit of cleaning up, a little bit of just chatting. I think I'd like to repair the Demon Core live on stream and get it working. There's some parts that are not working, so we're going to take it apart a bit and make sure it works before we finish the segment. It would be nice to get the Demon Core working. Jeremy, your first viewer. The poor Crather, the poor Crather. That's what we say. But you chat are saying that's not a real skull. She 3D printed it. Did you guys see me 3D printed though? Cleaning up a few bits and pieces. Ah, from Hawaii. What time is it in Hawaii, Shuffle? Is it like really late or really early? I'm confused. Well, we have a screwdriver hanging on the edge already. Oh, you guys don't see it, I guess. There's already a screwdriver there, but it's completely exposed. Yeah, we're just going to try and repair it because it's supposed to glow when it becomes radioactive or supercritical. So we need to fix it. I guess you would be surprised with a yes answer. Let's move a few things. Where's my box? My magic box. Just clean up a little bit to make a bit of space. Bum ba bum, bum ba bum. Bum ba ba bum. Thanks for the piece. Absolutely, absolutely. Thank you so much for hanging out, and I really appreciate all the gift subs and all the unwilling lab rats that joined us. And yeah, there's so many people who subscribed as well and contributed to the PP contribution. Weird sentence to say as always. So what we're gonna do is I'm gonna repair this demon core because for some reason it's not working. You guys get to see it in action a little bit. Oh, sorry. I'm gonna bring the camera down a little bit so you guys can see a bit more. But yeah, to anyone coming in, we're finished the physics, Irish physicists section of the stream. We have still under 2 hours left, so I'm going to repair the demon core. We might play games. So yeah, that's something that I do. If anyone's following this channel, you guys are more than welcome here. But I don't just teach physics. I teach physics, I build robots, I build electronics. Most of my stuff is I'm learning. I'm not an expert. I don't know anything about programming. I don't know anything about electronics other than theoretical stuff. And it's just about putting things together and learning. So you're more than welcome to hang out and teach each other and me, as long as you're civil and polite. That's the general rule.
Gee, Rain, what do you want to do tonight?
The same thing we do every night, Pinky.
Try and take over the world. What games? So at the moment I'm playing Dyson Sphere Program and I just finished God of War Ragnarok. I mostly play PC games. Actually, I exclusively play PC games. But as of recently, let me pull everything out actually. You aren't wearing any green. I'm not, no, but I have a lovely green border and I have an awesome outfit.
To commit no mistakes
and
still lose. That is not a weakness.
That is life.
That is life.
Do you know, surprisingly, I don't need to wear green to remind myself that I'm in Ireland. Shocker. I know. Yeah, so Dyson Sphere program or project has been really fun, but last stream, it really terrified for me. Do I have green socks? No, blue socks, sorry. It really terrified me because I have a fear of traveling in free space, three-dimensional space. And when that ended up happening in my last stream, I almost rage quit it. So I don't know if I'm going to play Dyson Sphere project anymore. program, sorry. Okay. What is this connected to? A bunch of this is the LED control. Okay. What pin number did I control the LED, I wonder? Let me boot up my real quick. And let me look at my code. Where did I pin? I need little stickers on this. File open. Demon Core final. Demon Core final. Demon Core, really, this is the final one. Ever heard of No Man's Sky? Yes, I've played loads of No Man's Sky. So No Man's Sky is very doable because why was I able to play No Man's Sky actually? It did make me uncomfortable at first. But I'm trying to remember what... Oh, do you know why? I play it on the Steam Deck. Remember I said that dissociation is needed? LED pin 4, by the way. In case I need a reminder. Remember I needed a dissociation. So when you're playing on the Steam Deck, you're kind of pulled away from the screen and it's very, very small. And so it's a lot more doable. The same thing happened with me with Subnautica. I couldn't play Subnautica on the PC, but I was able to play it on the PlayStation on the couch. Digital pin 2, digital pin 4. There we go. Okay. He was an Irish saint, but I don't know if he was Roman now. He came from the UK. Well, it wasn't the UK back then. But yeah, yeah. There's a very interesting story behind him. He is the patriot saint of Ireland. He spread Christianity everywhere. The classical shamrock is the depiction that he used to teach Christian religion. Like, what do you mean there's only one God? Yet you call him the Father, the Son, and the Holy Spirit. And it turns out that the stem is God, and each leaf of the clover, the 3 leaves, are 3 parts. That's what he taught and spread around in Ireland. Okay. Wait. Oh no, it's fine. I was going to say my sound sensor isn't plugged in. There's no digital signal, but I think it's because it's an analog signal. Don't want a digital yes, no. We want it like by how much the sound. Hopefully this works actually. Let me plug this in. Oh, patron saint. Yes, sorry. You're going to learn that English isn't a very good ability of mine. I literally had someone in the chat earlier. I was teaching all these different fields of physics. And someone came into the chat to say I know nothing because I forgot the name of 2 things. Forgetting the name of 2 things and not knowing what it means. Ah! Ta-da! My demon core works! She's alive! She's alive! This is a demon core. It is a project that I built all by myself, with the help of chat, of course. Chat definitely helped me with the programming, especially. Oh, there's a little hole here. Grab the nano, and we plug in the nano through this way. There we go. Is there a screwdriver to go with it? It'll be nice to create little storage things for a screwdriver. IDE, Arduino IDE, which is based on C++. we go. That's my PC. That's it. Yeah, donkey. That's it. That's it. But it's a model. It's a model of the Demon Core. So it was a major incident of huge radiation released as people were developing and building the atomic bomb. And the idea is when something heavy falls on it, it goes radioactive. And I don't know if you can hear it, but there's a Geiger counter sound effect as well. But there we go. I tuned out to drive home. I bring the stream back up and the Demon Core appears. Excellent, excellent. So yeah, I have 2 YouTube videos if you guys are interested in. One on how I built this, and number 2, what is the Demon Core? If you guys don't know what the Demon Core is and the history behind it, I use this as a teaching tool. So I'm going to university. Oh shit. I'm going to university on Thursday for a special segment where we bring in kids and teach them physics, you know, science communication, all that. And I teach something called A Brief History of Physics, where I go all the way from Newton all the way to the atomic bomb in a span of 20 minutes. And there's demos and explosions and everything's flying around. And I conclude with a Demon Core this year. And it's, yeah, to explain the dangers of atomic... Well, nuclear physics, but just because it's dangerous doesn't mean it's not useful. Yeah. Move very carefully over here. Have it working on screen. And that's how the Demon Core accident happened. Accurate depiction. Accurate depiction. The famous historical... Okay, whatever. I'm just closing you. All dead. Whoops. We dead again. Yes, lab rats don't survive very long around me for some reason. I wonder why. My wrist. Please do not drop the Demon Core. Yes, demons were released. I have a lot of demons that get released, especially Maxwell's feckin' demon. I'm so sick of Maxwell. Goddamn Maxwell. Just checking a few emails. Oh no, it's not a work day. Why am I doing that? I thought, oh, it's a work day. It's Tuesday. I need to check my emails, but it's fine. Today's a day.